Hello, everyone. Welcome to our third workshop on sensing, understanding, and synthesizing humans in this ICCV 2021. I think it's a great honor for us to organize this workshop and hosting a lot of amazing speakers and training sessions. Okay, next slide. Okay, so here's kind of the time schedule of this workshop. We have 4 hours. First, a very quick opening remarks, then the invite talk by Professor Andres Geiger. Then we have MVP Point Cloud Challenge briefing. We have our winner announced, as well as the sharing session of the winning solutions. Then after that, we will have the Forgery Net Challenge briefing that is going to detect deepfake images. Then after these 2 briefing sessions, we will have an invite talk by Professor Angel Dai. Then we have a 10 minutes coffee break. After that, we have another sharing session about building infrastructure for 3D human recovery that covers both code bases and datasets for 3D human recovery. And finally, we'll have an invite talk by Professor Hao Su, and we will just close this workshop. So the purpose were kind of the theme of the workshop is kind of centered around these 3 different ideas. The first is that we would like to take more holistic view on the integral pipeline of human sensing, understand, and synthesize. So nowadays, both the kind of the sensing technology and the synthesize technology have advanced rapidly, and there's a lot of like intersections among them. So it's very exciting areas that we should definitely keep an eye on and discuss more. The second idea is that nowadays the vision is going from 2D to 3D. A lot of like problems that is hard or ambiguous in 2D have some promising solutions in 3D. And 3D vision also requires more different understanding of our learning systems. Finally, is that we want to go from passive vision to active vision. So previous vision tasks generally is just sit and perceive, but now we like our intelligent agent to also explore the world while understanding what is structure and what is kind of the goal of the world. So that is kind of the transformations of fields. I would definitely like our experts to share their thoughts and discuss their recent work on this. Okay, I think next we'll just have our invite speak session. I will hand over to our organizer, Tong Wu.
Okay, thank you, Ziwei. So our first speaker is Professor Andres Geiger. Hi, Andres. You could start preparing, and
hello.
I'd like to give, hello, hi. Thanks for joining us. And I'd like to give a brief introduction for Andres. He's currently a professor at the University of Tübingen and the MPI for Intelligent Systems, heading the Autonomous Vision Group. He's done like really amazing works on 3D scene understanding, reconstruction, motion estimation, and of course, generative models, including the best paperwork derived in CVPR 2021. And he's also the creator of the Kitty dataset, which has just received the ICCV 2021 Avery M Prize. So congratulations. And they just released the recent Kitty 360, which could be of like really big contribution to the community. So it is really great pleasure to have you here. So Andres, please take over and show us some latest works in your group.
Thank you very much for these kind words. So I'm trying to share. Okay. Can you see this?
Yes, perfect.
Okay, good. Welcome everyone to my talk, which is on generating animatable human avatars. In fact, I haven't been working on human bodies for a while. This is the last time I have been working on human bodies. It was in 2008 for my master thesis, which I did with Raquel Urtasun and Trevor Durrell, and where we wanted to, where we built like new machine learning models for dimensionality reduction. Gaussian process latent variable models were in fashion at the time in order to track and classify actions of a person operating in a kitchen environment. Now, of course, things have advanced, and this work that I'm going to talk about today wouldn't have been possible with an amazing set of collaborators. The first work is SNARF, differentiable forward skinning for animating non-rigid neural implicit shapes. And the second one is meta-avatar, where the goal is to learn avatars really fast and with just a few 2.5D observations. So here are all the people that have contributed to this. And in particular, I want to highlight, of course, the people that did most of the work, Xu Shen and Xiaofei Wang. Maybe you can quickly turn on your video and say hi. They are here today and they will take over the hard questions at the end of the talk from me.
Hi, everyone. Yeah, hi, everyone.
Great for joining today. Okay, and then of course all the others. This was joint work with Michael Black from Max Planck Institute and Ottmar Hilliges and Xiao Tang from ETH Zurich. So let's start with SNARF, differentiable forward skinning for animating non-rigid neural implicit shapes. And yeah, so here basically we tried to combine the expertise of all the different groups. Michael and Ottmar are really experts on human body modeling, and we have done work on implicit human representations. And so we're trying to combine the best of these worlds here. Right? This is the goal. So how can we create avatars with neural implicit shapes? And why are implicit shapes actually useful? Well, neural implicit representations are useful for 3D human modeling, we think, because they allow for flexible topology, because they are representing shape implicitly, and they are also resolution independent, which means that the quality of the output reconstruction is mostly determined by the architecture and the capacity of the neural network. So just as a little recap for those of you who haven't heard of these models before, what is it all about? Well, a neural implicit representation is nothing else than, in our case, a classifier. This is a neural network here that takes in a 3D point and outputs a probability of occupancy. Basically tries to predict if that 3D point is inside the shape or is it outside the shape, right? So we have learned a lot of models that predict such class or that train such models, such classifiers for static shapes. But here we're interested in dynamic human avatars. And then once we have such a model trained, once we have the parameters of this network, we can of course extract the surface of that shape, which we are interested in typically because we can convert this into a mesh. We can extract this by finding the level set of this classifier, the decision boundary, where the decision is exactly between inside and outside. This should be the surface. And this is an example here of such a surface. Okay, so very simple. The neural network itself is the representation. There's no voxels, no meshes, nothing, no points. It's just a neural network that represents through its parameters the shape. Okay. However, well, while this works really well on static objects, animating them is not straightforward, animating these neural representations. So the goal here is to generate implicit shapes in given poses. Illustrated here. So here we have a model that takes in a 3D point and a pose and outputs then the occupancy for that 3D point in a particular pose. Also, we want to learn the shape representation from deformed observations directly, because we don't want to assume any additional supervision, for example, on the skinning weights or something, which we typically don't have available. We want to train it all end to end, just from observations of the posed models, which are coming from our 3D scanner. Right? This is all we have. It's all unsupervised in that sense. So the key question is how to model and learn skeletal deformations of implicit shapes most efficiently. And of course, inputting them directly as a condition is not a good idea. It doesn't work very well. So we need to use some of the interesting and nice machinery that people in human body models have developed. So let's look at some existing solutions. for animating implicit shapes. And this is, of course, a very prominent one. It's called NASA, from Deng et al. At ICCV 2020. NASA is a piecewise rigid model, which models the shape as being composed of parts, which is, of course, a good idea, right? Human is composed of parts, body parts, and each part in this model can be rigidly transformed. So here's an example with two body parts. Think of this as like the lower leg and the upper leg or something like this. And then there's a rigid transformation that transforms these two. And then there's a composite operation that composites them into a deformed shape that is then compared against the ground truth. And if that overlaps maximally, then we have a good representation. The problem with this model is that it is not very accurate at joints. It leads to really gross artifacts at joints because it has this rigid transforming and composite operator that together cannot represent like how the shape complexly deforms at the joints well. So you can see this here also, right? It doesn't represent the region at the joint well if the object is deformed. Another approach to animating implicit shapes is backward skinning, which has also been explored in the past, for example. In backward skinning, the idea is to learn a backward linear blend skinning model, a standard linear blend skinning model where you have the input is the bone transformations basically. And then for a point in deformed space, you pass that through that linear combination of bone transformations, basically weighted by the skinning weights in order to arrive in canonical space, right? This is illustrated by this arrow. The problem with this is that now the skinning weights are pose-dependent, obviously, because you're modeling the skinning weights in the post space, and because the pose varies, this skinning weights are very complicated to learn because they are really depending on every pose, and this doesn't generalize very well. If you have just a set of poses in your training set and you want to generalize to new poses, of course, your skinning network doesn't know how the skinning weight should look like for the new poses. So it doesn't generalize to unseen poses, and also it cannot handle one-to-many mappings. So if there is a point, because this is a mapping that maps one point in the skinning in the post space to one point in the canonical space, you can't model one-to-many mappings, which often are desirable. For example, think about body parts that are touching each other, right? If I have the hands, both hands touching each other, and I want to query a point that's in between, then it could be a point belonging to one hand or a point belonging to the other hand. But of course, this model must commit. It must commit to one particular point in canonical space, right? Which is not ideal and leads to problems. And this is illustrated here. So for example, here, this is exactly such a model trained actually in a 2D toy scenario, where we then observe that even for this very simple model, backward LBS doesn't generalize at all. So here it deforms the shape while the ground like this, while the ground truth looks like this. And the reason is that this skinning weights don't generalize, so the point is projected to the wrong location. Okay. So the idea in this work is therefore to use forward skinning, which is of course very natural, and that's also what we like to do, but it's harder to learn because what we need for learning, I mean, we have just post observations, so we need the inverse function of the forward LBS, not the forward LBS. But the nice thing about the forward LBS is, this is how shapes are normally animated, right? Also meshes, is that now the skinning weights, they are represented and they can be learned. We don't know them, but we learn them. So they are represented in canonical space, which means they don't depend on the pose, right? The pose is in deformed space, but in canonical space, we always have the same shape, well, subject to like dependent corrections, but roughly the same shape. And so the skinning weights don't need to change. Right. So the forward LBS has pose independent skinning weights, and that makes it really much easier to learn, and also it generalizes much better because now I can deform the shape into an unseen pose because the skinning weights are defined in canonical space and don't need to deform with the pose. So you can also model novel poses. It's illustrated here, exactly the same case from before, but now a much better approximation to the ground truth. Okay. So we can generalize better to unseen poses, and we can also handle one-to-many mappings now because we're modeling this mapping in the forward direction. Of course, a function in the forward direction, when we invert it, can represent a one-to-many mapping. So exactly like if two hands are touching each other, I can map to two different points at the same time in canonical space. But the problem with this is, how can we learn this actually, right? Now we don't have the backward mapping explicitly represented. It's only implicitly represented for the forward LBS. And still, we just have observations in post space. So we need to learn, we need to somehow invert this model in order to query for if we want to update the geometry, for example, right? We need to, for any point in post space, for a particular pose, we need to find the correspondence in the canonical space. So we need to invert this model to get back from the post space to canonical space. Yeah, and so this is how we do it. And the idea is very simple. We invert it by a numerical iterative root finding procedure, starting at an initial guess and then just numerically finding a root. Okay, so how does this work? This is basically correspondence search. So we start with a point. This is in post space, as you can see. This is canonical space. This is the standard T pose. This is in post space. So we want to, for this point here, and this is exactly the scenario that I sketched before. This is a point where two body parts are touching. So we want to find this correspondence here in blue and this correspondence in green, because it could be both, right? So one-to-many mapping. So we're given this point in post space, and we call that X prime, right? And what we know is that for the correspondence of X prime, which we call X star, if we pass that correspondence first through the skinning weight field so that we get the skinning weight, and then we pass it through the forward LBS, this is here in blue, here it's called D, so this is the forward LBS, then we must arrive at X prime. So we take either green point or the blue point, compute the skinning for these points, the skinning weights, and then pass it through the LBS given the current bone transformations, given the current pose, and then we have to arrive here from either of these points, right? So we can do now the opposite by looking at this equation here. This is just the equation of the forward LBS, and of course, if I subtract the post point, then I must arrive at 0 because the forward LBS must be equal to the post point. Can now try to find the root of this function numerically, right, in order to obtain X star. But the question is, where should I start optimizing X star? There's multiple solutions, right? And that's exactly where the multiple solutions come in. What we do is we simply apply root finding with multiple initializations. So we rigidly transform this point here with each bone as initialization. Let's say the body has 24 different bone transformations. So we take all 24 and we transform this point 24 times. And these are potential corresponding initializations, X star or X. X star is actually the solution already. And then, so we have the initialization now, X0. And then we apply this iterative root finding for each of these initializations, and we collect the valid solutions, which is the set of all X stars for all these 24 that arrive at the point that if I then apply the forward skinning model, the forward LBS model, I retrieve X prime again. So there might be some cases where this simply diverges or it doesn't converge, and so it doesn't arrive at X prime, and we throw them away. But all the others that arrive at X prime, where then the forward process is correct, we keep. And this is the set X star. In this case, for this red point, we have retrieved the blue and the green point. And now, because we have, of course, now for this post point found the point in corresponding canonical space, now we can simply query the occupancy network in canonical space in order to get, for each of these 2 points, a occupancy value. And this network can be post-dependent to model post-dependent deformations now in canonical space. And now we have one of these occupancy predictions for each of these points, and we combine them using the max operator by simply taking the maximum. If it's occupied in any of those, then we say it's occupied, and this is the final occupancy, right? And we compare that occupancy against the ground truth occupancy. We assume we have watertight meshes, so we have ground truth occupancy, and then we can train the model by back propagating through this entire process here. Okay, so here's the training objective. We use a standard classification, binary cross-entropy loss. We have watertight meshes. We know what's inside and outside. We can train this model just from using standard binary cross-entropy. But we observed it's beneficial to bootstrap it a little bit by, in the first epoch, adding 2 additional losses, the bone loss and the joint loss. The bone loss says, well, we believe that everything that's on the bones, any point on any bone, is inside the human body. And that helps bootstrapping the model. And similarly, we can say, well, at the joints, we believe that the skinning weights should be something like 0.5 for the one part and 0.5 for the other part, which we call target here. So this is a big vector, which is 0.5 into elements. So this helps to bootstrap the model, so it becomes more stable at optimization, but we need it only in the first epoch, and then we throw it away because actually this is a bad inductive bias. It biases our model towards a bad heuristics, and so we throw it away to let our model freely optimize. The analytic gradients can be derived via implicit differentiation, similar to what we do, for example, in DVR, differentiable volumetric rendering. I'm not going to go through the details, but basically, given a point on the surface, we can, through implicit differentiation of the level set constraint, we can derive the gradients of that surface point with respect to the parameters of the networks. And we optimize here the parameters of both the skinning weight network and the occupancy network in canonical space. So both of these are unknown. We just have the observations in post space, and we optimize the skinning weight network and the occupancy network in canonical space. So let's look at some results. This is results on the DFAUS dataset. So here we first see some samples on the DFAUS dataset. And here are reconstructions of novel poses within the training distribution. So now the poses that we reconstruct are coming from the same distribution as we have trained on, and the baselines are backward skinning, NASA, and here we compare ours against these 2 baselines and the ground truth. Ours is the 3rd column. And you can see that even for within pose distribution samples, the backward skinning baseline struggles. If we go outside the training distribution, these are now outside the training distribution. For example, this bridge pose here, we can see that the baselines completely fail in reconstructing that, because they can't generalize as well as if we have a model that models the forward LBS. Here are some examples on clothed data, CAPE dataset, with meshes obtained from 4D scanner. These are training samples. Here on the left, you can see the learned skinning weights. And now on the right, the reconstruction for novel poses outside, again, the training distribution. So these are OOD examples here. You can see that it leads to a quite nice shape when animating. Yeah, so it's pretty neat that we don't need to specify the LBS weights by hand, but we can just optimize for them. And we don't need a very good initialization, but it just comes out automatically from the data. Okay. So in summary, I've presented an approach that performs differentiable forward skinning. In other words, learns a forward skinning and shape fields in pose-independent space. And it learns from the formed shapes without direct supervision or prior. So no direct supervision on the skinning weights, and no prior, for example, in the form of a simple body model. So it can also model clothed humans, for example. It generalizes to challenging unseen poses at test time as well. However, the root finding procedure is quite time consuming, also because we have to do it for every bone transformation, for every initialization. And each iteration requires a skinning network query. It also requires full 3D data, right? We assume like we have watertight meshes, which we can query inside and outside. So it would be nice to combine this in the future with a differentiable renderer to learn from image directly. Also, it requires accurate poses for training. So what we'd like to do is, of course, jointly optimize pose, shape, and skinning. At the moment, we just assume accurate poses are given. And if you don't have accurate poses, it doesn't work so well anymore. And so far, we have considered overfitting to or training for one single subject. And of course, it would be nice to exploit a model that works on multiple subjects so that we can generate also novel avatars. And like the last step on this last point and the second point are addressed in the next work. So how can we train models across multiple subjects that then fine-tune very quickly to a single subject, and that also don't require this full watertight meshes and 3D data for training. Okay, so this was the first part. So let's look at the second model now. That's called meta-avatar, learning animatable clothed human models from few depth images. And it's going to be presented at NeurIPS later this year. The goal here, in contrast to the previous work, is to obtain controllable avatars learned from few monocular depth observations in little time. Here's an example. Given just these 8 2.5D depth observations, we're obtaining an avatar for this person that we can then animate in and pose in novel poses, in novel unseen poses, and that looks quite realistic despite this sparse and noisy inputs. And here on the right is another example. So the key here is that no full body scans, like in the previous approach, or per subject clothes type optimization from scratch are required, which is very slow typically. Like also the previous model required quite some time for training for a single person. Here we can train in very little time. In particular, with only 8 depth maps as input, we can train this model in just 2 minutes. We can generate an avatar in 2 minutes only. And the idea in order to achieve this is to meta-learn a post-conditional hypernetwork to predict the parameters of a neural SDF. Now this sounds very complicated, but it's actually not. And we're going to go through this step by step. We want to meta-learn a post-conditional hypernetwork to predict the parameters of a neural SDF. Okay, so here is the general high-level gist of the approach. Using a learned inverse LBS, so in this case, the linear blend skinning is assumed to be available. Unlike in the previous model where we have trained it jointly, of course, it would be nice to do it here as well, but in this first step, we have assumed it's available. It has been pre-trained. Using a learned inverse LBS, we assume both the inverse and the backward and the forward LBS are available. We transform the input depth maps into canonical pose, right? If we have this and the poses, then we can transform them. So we assume we have both the LBS model, the blend skinning model, and also the poses available. So we can fit a pose, we can run a pose estimator on these scans, for example. Okay, so now we have canonicalized them. Once we have them canonicalized, we fine-tune a pre-trained meta-learned hypernetwork, it's illustrated here, for that particular subject that gives us a subject clothes type specific dynamic SDF representation. So this hypernetwork predicts the parameters of the neural SDF, and we fine-tune the hypernetwork's parameters in order to obtain this model. And then given novel poses, here illustrated by the bone transformations B, we can then generate novel, like this subject in novel poses. And these generations are also pose dependent. So basically we model like the changes in wrinkles and so on. So we get pose dependent animated meshes. Okay, so how can we go about this? The simplest idea would be to just meta-learn a neural SDF model. So in this case, we are not predicting occupancy, we are predicting sign distances, but essentially it's the same thing. So it's a multi-layer perceptron. In this case, we use a siren that has sign activation functions. It's a multi-layer perceptron where we input a 3D point, and the output is the sign distance value to the surface. We use a siren network with 5 layers and 256 neurons in each layer. Mathematically, we denote this as f phi of x. Phi are the parameters. In order to train this model, what we can do is we can use a point-based on-surface and off-surface loss, similar to what has been proposed in Gropp et al. So this is in order to make this model train from these point clouds alone without having inside and outside observations. So we can train with an on-surface loss using the iconal equation. And then we can meta-learn the network parameters, this one here, on all subjects that we have in the training set using a meta-learning algorithm. And we use Reptile, which is a very simple meta-learning algorithm. The idea is basically you want to have a parameterization of this network that's good for all subjects. You want to basically, you train for a couple of gradient descent operations on each subject and then find kind of the average of these parameters, such that when you get a new subject observation, then you can fine-tune very quickly to that. That works very well. Yeah, so this allows for fast fine-tuning on new subjects, but it doesn't obviously model pose-dependent deformations, right? Model that we can apply this in the canonical pose, in the canonical space, which is fine. So we have abstracted away the pose, but then we can't model pose-dependent deformations, which we would have to model also in canonical space. If the body, human body changes, then we're like the shape also changes in canonical space a little bit. So these correctives we can't model here. But we can pose it to a new shape and see what it looks like. Right. So in order to improve upon this model, of course, we can also meta-learn a pose-conditioned sign distance function. Again, we have a 5-layer siren network with 256 neurons in each layer, but now this network is conditioned not only on the input 3D point, but also on the pose parameters. Again, this is a model that's modeling the canonical space, right? We assume that we have an inverse LBS and a forward LBS, so we can do the posing in both directions. So we just need to model in canonical space. But now in canonical space, we can model pose-dependent correctives as well, because we condition on the bone transformations. However, we observed that this baseline, the simple baseline, does not work very well and leads to overly smooth results. So here's an example. On the left, you can see the results of the meta avatar model that we propose in the end. And this on the right is the meta multi-layer perceptron siren model. And you can see that it's in many areas, it's smoother than we want it to be. And that's also something that is expressed numerically. So what we propose to do instead is to meta-learn a post-conditional hypernetwork. And that actually works better. The idea is to learn a hypernetwork G, this is the top part here, that predicts the parameters of the siren network. This is why it's called a hypernetwork. And the idea of hypernetworks have, of course, been explored before as well, but not in the context of dynamic SDFs for generating avatars. So the hypernetwork takes as input the pose and shape parameters in the form of bone transformations as input to the MLP of the hypernetwork, and predicts the parameters in each layer of the siren network. Now, what we found important is that the hypernetwork predicts not directly the parameters, but the residuals to the meta-learned SDF parameters phi star. And this is illustrated here. So this SDF has as parameters the parameters predicted by the hypernetwork plus the parameters of the meta-learned SDF. This is the first model that I've shown you, this model here. So we train this model without considering pose-dependent correctives to get a rough idea of what the shape should look like in canonical space. And that is a good bootstrapping for us, makes the problem simpler. And then we can, this model here just basically needs to learn the difference, which are the pose-dependent correctives. So that works better. And then at test time, what we need to do is we simply need to fine-tune the parameters psi of the hypernetwork and then obtain a avatar model for the observations at test time. Right? So we pre-train, we meta-learn both these parameters in the first stage and then these parameters psi in the second stage, and then at test time, we fine-tune these psi parameters of the hypernetwork to get the avatar. Okay, this looks a bit complicated, but it's really not. Let's look at some results. Here we have results when learning with raw sensor inputs. On the right, we can see the inputs. And in the middle, we see the output of the model in canonical pose and then in post space. You can see how the pose changes now. You can see the pose correctives. You can see how the pose affects the shape in canonical space. And that this is also, of course, necessary to get a realistic outcome in post space. Now, this was done on, 3D scans projected into 2.5D. But of course, we can also try this on Kinect data directly, which, as you can see here from the left-hand side, is much more noisy than the nice scans from the 3D scanner. But still, we can do that. If we estimate the poses correctly and we get the blend skinning models correct, and this is what we get out of this. Of course, it's not as precise and not as accurate anymore. For example, if you look at the facial details, but overall, we obtain still a reasonable avatar. This is to demonstrate how much performance drop we observe when we reduce the amount of data for fine-tuning. So here on the top left, we use all the data that we have available for fine-tuning, then 50%, 10%, and only 8 to 20 frames, depending on the subject. And you can see that while the performance degrades, we still get reasonable results with just few frames. And this is really important, of course, if you want to learn such avatars in a consumer setting where you ask a user to capture a few images. The user doesn't want to capture hundreds of images, but just a few images are enough to get such an avatar representation. This is also illustrated here. What you see here on the x-axis is the percentage of data that we use, and we don't get a big drop in performance when we use less data, but we get a big speed up. So here's the training time, fine-tuning time, basically in minutes. And we just require between 1 and 5 minutes for fine-tuning, with between 1 and 20% of the data, which works reasonably well. And this is an improvement of over 2 orders of magnitude with respect to, for example, NASA, that has to train a model from scratch every time for every subject that it trains on. So this is the advantage of hyper learning, of meta learning. Okay, and here are some comparisons to baselines. So what you can see here on the top left is our meta-avatar results, then on the top right, Scanimate, which uses artificial hands and feet, and which requires full body scans. Here on the bottom left, Leap, and on the bottom right, NASA. And you can see that despite meta-avatar is using only 2.5D inputs and can work with very few inputs and trains very fast, the avatars that we get are on par or better than what the baselines are able to produce. Okay. That brings me to the end. So I presented in this second part meta-avatar, which enables generation of controllable clothed human avatars and allows for fast subject-specific fine-tuning from just a few depth images. It enables realistic clothed avatars, generation of clothed avatars in only 2 minutes from as little as 8 depth maps. And I've also shown that this hypernetwork idea is really required to capture fine and detailed pose-dependent deformations. However, the model currently needs learned inverse and forward LBS models and also bone transformations as input. And this would be, of course, nice to lift this restriction more and also to model not just the shape, but also the appearance. That's all from my side. I want to thank again Shu and Xiaofei for this fantastic work. And yeah, we are looking forward to your questions if you have any.
Okay, thank you. Thank you for the very inspiring talk. And let's see if there's any question from our audience.
Just put them in chat or speak up if you have any. Let me bring that up here.
Hi, Prof. Geiger. This is Junzhe here.
Hi.
From NTU under the same lab as Prof. Ziwei. Yeah, so
nice to meet you.
I have a question. Yeah, I have been following your work since the texture field. So I'm asking one question, I think not really out of your radar. Yeah, so basically, would you think combining the texture for the animated human or avatars is something trivial or worth exploration?
Well, I mean, it would be kind of easy to put a texture field on top, but the registration, like the problem with the texture is that the pose and the geometry must be super accurate in order to avoid like smoothing out texture details, right? And to get really, like what's really challenging is to get really crisp and nice textural details. I don't know, maybe Xiaofei wants to also comment on this. I think you have already explored this a little bit, or Shu also. Do you have any experience with appearance, and what are your insights here?
Yeah, like my experience is like you really need to have a very good geometry, and you need to condition like your texture field, let's say, on the good geometry. Then you can get some reasonable texture on the generated avatar, because now like for both of work we are focusing on this generation on novel poses, right? So yeah, it's like it's more about like generalization. So it needs a kind of good geometry, and it needs good data, which is kind of hard to get actually.
And sometimes you have unobserved areas as well, right? So you need to in-paint, like if like you're like in the trainings that you have, that like maybe below your arm there's no observation, right? And then you need a model that is able to reconstruct that, because otherwise what you have is like you just get something black, or the model is producing something random, blurry there, and doesn't look very good if you repost that into something novel.
So let me just trying to rephrase, see whether I understand that correctly. So in terms of the texture, like sometimes we need to have some hallucination, like for those like the invisible parts, for example, we would like to observe from a single image, then the backside or those observed occluded, that can be very hard to guess, right? So this is one. And point two from Xiaofei, I think basically this requires something like the texture fields, which requires pre-trained like occupancy night behind or adjust geometric ground truth before you trying to learn the textures. Is that true?
Yes.
No, you can train it jointly also, right? I mean, you could train it jointly if you wanted to, or you could first train like the meta avatar and then try to add the texture on top. But the geometry must be very precise, no?
Yes. That actually was what we briefly tried for meta avatar. Want to try the texture on it. Yeah, but the conclusion is that it needs to condition on the like good geometry like feature, like output from the SDF. You cannot just have a texture field and to predict things like with no conditioning. That's very hard. And and if you require good geometry, then you need very good like data, like have a really well aligned texture or well aligned image and geometry.
Okay, yeah, understood. Thank you so much.
Thank you for the question. There's also a question for you, Xiaofei, in the chat. I wonder meta avatar's performance on some other cases, like a man with an overcoat or a girl with a long skirt.
Yeah, that's something we would like to try, but at this point we don't have such data on those special clothing types. But I would say like with skirt, we might need some improvement, like this whole like canonicalization in the star pose and skinning network, like and this skinning prediction in canonical pose, it has some shortcoming. Like if you have skirts, it probably will fail on skirts, because like the skirt is kind of lying between the two legs in the canonical pose, And yeah, it's kind of hard to predict skin image for that part. If you check the Scandinavia paper, they did something similar. They tried something similar, but they failed. It said this kind of, this forward scanning doesn't work very well for skirts, at least.
Yeah, that's a problem, I think, still. And skirts are also like very stochastic. There's many solutions that are good, but you don't want to average them. Then it doesn't look good anymore. Yeah, so I think it's unsolved, probably. So there's some more questions in the chat.
Okay. What loss is adopted? Yeah, so the loss is not, the loss is it's basically the implicit geometric regularization, that paper. We copied we just copied the loss from like the paper Andres mentioned in the slides. I think
IGR.
Yeah, the IGR loss basically it's like has some unsurfaced loss, which is to say those unsurfaced points should have a 0 SDF, and you randomly sample some point in a space. So for randomly sampled point for random sample in a space, it has very low chance to be on surface. So it can be considered as off-surface loss. You just have some loss to push those random points away from surface, like set their SDF to be non-zero. And also you have this orthogonal term basically saying this gradient of the SDF with respect to the input coordinates. The norm of this gradient should equal to 1. That's basically the 3 loss terms. But you can check the paper.
I have a follow-up question for this. So during this fine-tuning, does this input depth views has to be roughly registered to a simple model so that you can have this notations of the bones? Okay.
Yes, you need to know the bone transformation.
So if this step fails, then the aforementioned steps will also fail, right?
Yes, it will fail. Like I think for most of the avatar generation works, they kind of rely on this more or less accurate simple registration.
Okay, I see. So by leveraging the simple registration, do you rely on the simple surface information? For example, because simple is a naked model. So if the input depth of the online human body is not close to naked, like his real long coat or skirt as mentioned before, so can your model still generalize well to these cases?
I think for the blazer jacket we showed in our paper, I'm not sure that kind of if that kind of looseness is what you expected. Like you can check the video. I think we already put the archive version video online. It's like we specifically shot this like this blazer jacket scenario, which you have this like a kind of loose tail of the jacket, and it's kind of you can see it's a little bit. It's kind of far away from actual minimum closed body, and it's still like a kind of generalized well. But yeah, for like even longer coat over like a skirt, for those we don't know because we currently don't have good data for those scenarios.
Okay, I see. Thanks for your answer. Thank you.
Yeah, thanks.
Thanks for the question.
Okay, I think there are still more questions. Like, I would like to hear your comments on that. What do you think is the key of the generalization ability for implicit function? Is hypernetwork or meta-learning the key for this, or generative model?
That's a good question. I mean, in SNARF, what is key is that we model the forward scanning, because then we can generalize, right? Because everything is in canonical space, and so we build in the inductive bias. In the second part, I don't know. This is maybe also a question for Xiaofei. Like, what do you think makes your model? What is the aspect of your model that makes it most powerful in terms of generalization?
In terms of generalization,
we don't have a generative model yet, right? So that's there's no generative model yet in these models. I mean, generative model is always helping robustness and generalization, of course, but
it's how to say, it's So it's not really that generalizable. I would say you still need it's kind of I would say all this kind of work is still kind of interpolating between the already seen poses. It's more like interpolating in the scene spaces. It's not. I don't think like this neural network is good at extrapolating in like without special design. If we just consider we have a big MLP and has some space to learn, it's very easy to interpolate, but I guess it's very hard to extrapolate like completely unseen scenario.
I guess for meta avatar, what is important for good generalization is to have like good LBS models, right? Because otherwise you can't if you can canonicalize any input and you can generate any output pose, that will, I mean, that's necessary. And then the pose-dependent deformations that we learn, I think that's what you just said, right? So there we can only interpolate mostly. We can't do excessive out of distribution pose-dependent correctives.
Yeah, I think a best case is just is find some nearest interpolation to already seen poses, and it doesn't. For example, if you like do this upside down pose, it probably won't flip your closest downside if you haven't seen that before.
Okay, I think there's another question from Zhongang. So, which is, would you mind sharing some thoughts for parametric model such as simple?
That's maybe you can make that question a little bit more precise. Not exactly sure where you're going with that question. Can you speak up maybe? What do you mean exactly? What is what are the thoughts that we should share about parametric models?
This is Zhong.
Thank
you, Professor, for the great talk. It was really enjoying listening to your recent progress. And my question actually goes to a bit like compared to other questions, a little bit more high level. So we know that your work are mainly on like implicit functions, and they are great in modeling the surface model of the people. And we are also quite interested in Prof Black's simple and the parametric models, which is like a more explicit way of modeling human surfaces. So we are quite interested to listen to your thoughts on like what do you think are the pros and cons comparing these two models and the prospect of the industry? Like what are the directions?
So from my perspective, I don't know, maybe Shu can correct me also if I'm wrong, but from my perspective, like for modeling the naked body, I mean, there's not that much wrong with using a simple body model, but when it comes to clothing, it becomes really hard with meshes, or if you want to deform a simple mesh into a complex shape where you have like complex topology changes. I don't know, Shu, do you have any good answer to this? Ideas, or also Xiaofei? I don't know.
Yeah, I also think so. Like this implicit function is pretty good at this model topological changes, like this loose closing. Yeah.
Let's say if we have implicit, parametric models for clothing, just in, let's say we have like 5 to 6 models for, let's say, short sleeves and long skirts. Would you think it would be much manageable to use parametric model instead of like a free model-free way of tackling clothing modeling?
I think there's already a mesh-based clothing model like CAPE, right? But if you check the result, you can still see, like, because they are still using limited amount of vertices, they can't really model very high fidelity details like these implicit functions. But you're right that they are more controllable and they are more like interpretable in a sense. So, and also they're more friendly to like these graphics pipelines, so people can directly use it. I think that's the advantage of meshes for modeling like closed human.
Thank you very much.
Thanks for the question.
Thanks for the questions and thanks for the answers. I think it's about time. So thank you, Andreas, Xiaofei, and Xu for joining us, and hope we can keep connection.
Thanks, it was a pleasure.
Thank you.
Thank you.
Okay, I think we can move on to the next section. We also hold 2 challenges in this workshop, which is multi-view partial point cloud challenge and the phase forgery analysis challenge. The organizers will give a briefing and will also invite some outstanding teams to talk about their approaches. So the first part is the MVP challenge. So Liang, are you there? Please take over and the floor is yours.
Okay, thank you, Wu Tong. Hi, I shared my screen, so can everyone see it? Maybe Wu Tong can help me answer.
Yes.
Okay, thank you. So hi, ladies and gentlemen. I'm Liang Pan from SLab Nanyang Technological University, and I'm going to provide a summary report for this MAP multi-view partial point cloud analysis challenge 2021. Okay. First of all, I will briefly introduce the MAP challenges. Then I will report the challenge results. Thanks to the fast development of 3D sensors in the past decade, we can conveniently capture 3D things by using LiDAR and depth cameras. However, due to imperfect measurements and viewpoint limitations, single-view observation is mostly partial and therefore cannot fully describe the whole 3D thing. To address these problems, we can perform point cloud completion based on a single-view observation. We can also use more different observations to achieve 3D reconstruction by performing partial to partial point cloud registration. For single-view partial point cloud completion, the target actually is to generate a fine-grained complete point cloud based on an incomplete point cloud observation. Because the incomplete point clouds are generated by using virtual scans, that is the depth maps, points for the scanned surfaces are often unevenly distributed. Also, incomplete point clouds can only partially preserve local surfaces, local structures, and which can lead to multiple different point cloud completion results. In this completion competition, we create a training set with 62,400 complete point cloud pairs, a testing set with 41,600 incomplete point cloud pairs, and an extra testing set with 59,800 samples. Note that the extra testing set is only for this competition due to a few limitations. And in this competition, we use chamfer distance to evaluate the competition results. Existing completion methods usually use chamfer distance as their training and evaluation metric, which, however, can often be biased to outliers and the observed partial point clouds. To achieve balanced and high-quality point cloud completion, we can think of designing better generative models, such as using diffusion model and or using better metrics instead of CD loss. In real applications, researchers usually perform 3D shape reconstruction with the help of some more observations by performing partial to partial point cloud registration. Nonetheless, P2P PCR partial to partial point cloud registration is very challenging for deep learning methods as well as optimization methods, especially for different noisy partial scans. In this registration competition, we create a training set with 6,400 partial point cloud pairs, a testing set with 1,200 partial point cloud pairs, and an extra testing set with 2,000 pairs. Likewise, the extra testing set is also restricted for this competition only. We use isotropic rotation arrow and isotropic translation arrow to evaluate the registration results. Point cloud registration actually is a long-standing problem, which suffers from incomplete observations, noisy measurements, and large transformations. Recent registration methods for 3D objects are mainly proposed based on ModelNet 40 dataset, and here we propose a more challenging object-centered dataset consisting of noisy virtual scans for pairwise point cloud registration. A few interesting questions remain, such as whether point cloud completion and registration can mutually benefit each other. So now let me introduce the MVP challenge results. In total, over 100 accounts are registered for this challenge. And in the hidden test, 10 teams submitted their methods. Thank you for your efforts. And one thing to highlight is that pre-train issue in the completion track, because our actual test dataset consists of those CAD models from the training set of PCN datasets. Then if you use a deep model pre-trained on the PCN dataset, will not be appropriate, as the testing samples are used in your training. And that is the reason we do not allow pre-train or additional data for training. And please only use the test data set in your future publication. So winners, the third place for completion. Congratulations, Junshen et al. From Tsinghua University and Wayne State University. The second place for completion. Congratulations, Ming Ye et al. From University of Chinese Academy of Science, Shenzhen Key Lab, Shanghai AI Lab, and Fudan University. Their method title is Robust and Discriminative Two-Stage Point Cloud Completion with Semantic Refinement and ROI Augmentation. The first place for completion. Congratulations, Xu Ming et al. From Tsinghua University. Later, Xu Ming will report their method, Pointier++, enhanced geometry-aware transformers with iterative refinement. Now comes to registration. The third place for registration. Congratulations, Qin Long et al. From Xi'an Jiaotong University. Their method title is RMNet, Partial Point Cloud Registration with Inliers Prediction and Matching. And the second place for registration. Congratulations, Li Fa et al. From Deep Glint, Shanghai Jiaotong University and Sichuan University. They propose to use deep model with fusion strategies. The first place for registration, Yuan Jie et al. From Nanjing University. Later, Yuan Jie will report their method, hybrid optimization method with unconstrained variables. So to give a brief summary, the trend for completion and registration. For future research directions, we can consider using semantic clues and geometrical primitives for completion. And new generative models and new metrics can also be tried in this field. For registration, we can think of questions such as how can we achieve efficient optimization with the help of deep learning, and how can we estimate reliable correspondences between different point sets. Now let's move. Let me save time for Xuming to present their method, or their team members to share their method. So Xuming, are you there?
Okay. Hi, Liang.
Hi.
I'm Yongming Rao. I will share our solution. Okay. Hello, everyone. I'm Yongming Rao from Tsinghua University. I'm pleased to present our solution for the MVP challenge, Pointer++, enhance the geometry-aware transformer with iterative refinement. Taking the incomplete point cloud as input, the point cloud completion task requires the model to predict the missing part. Here are some completion results produced by our method. There are two key components in our solution. The first is the base completion model based on our previous work, Pointer. The second is the newly proposed iterative refinement block to produce a high-quality completion results. Pointer is a transformer-based model to address the point cloud completion problem. We reformulate the completion as a set-to-set translation problem. The Pointer model consists of 5 key components: a encoder-decoder architecture to convert the point cloud completion as a set-to-set translation problem, point proxy to represent the original point cloud as a set of feature vectors, and the geometry transformer block to help the transformer to better leverage the inductive bias about the 3D geometry structures, and the query generator to dynamically generate queries for the decoder and the multi-skill point cloud generation process to generate the final prediction in a close-to-fine manner. The transformers in NLP task take a 1D sequence of word embeddings. To make 3D point cloud suitable for transformers, the first step is to convert point cloud to a sequence of vectors. There are 3 steps to extract the point proxies. We first sample a set of local centers using furthest point sampling. Then we use a Litecoin DGCNN model with hierarchical downsampling to extract feature of the centers. Lastly, we add positional embedding to the local features. One of the key challenges of applying transformer is the self-tension mechanism in transformer locks some inductive bias about the structure of the point cloud. To help point transformer to better leverage the inductive bias about 3D geometry of point cloud, we designed a geometry block to model the geometry relations, which can be a plug-and-play module to use in many transformer models. To predict the point proxy of the missing part, we propose to use dynamic query embedding, which make our decoder more flexible and adjustable for different types of objects and their missing information. We also propose a multi-scale point cloud generation framework to recover the missing point cloud at full scale in a cost-effective manner. Oh, sorry. Sorry. Let me see. Sorry. Yes. There's some problem with my point cloud, with my PowerPoint. Let me show. To predict the missing part, many previous methods like PCN and TopNet use reconstruction pipeline, encoding the input point cloud as a single feature vectors and reconstructing the point cloud by a decoder model. While the pointer adapts the concatenation strategy, where the final prediction comes from the concatenation of the input and output of the model. The conjunction framework produces smooth and continuous predictions, but it may cause some information loss. The concatenate framework can fully preserve the details of the input, but there may be some density difference between the two parts. This is an example of the point cloud produced by our pointer model. We see the result is good overall, but there is some density difference between the input point cloud and the prediction cloud. Therefore, we propose the pointer plus, which extends the original pointer framework with a concatenation refinement pipeline. We add a reconstruction module to the output of the pointer model to further refine the result and make the final prediction smooth and continuous. To preserve the details of the input, we only predict the position shift vector for each point cloud in the refinement block. The new pipeline combines the advantages of the two kinds of model. We also propose an iterative refinement method, which iteratively refines the point cloud using several refinement blocks. We iteratively add the refinement block after the base model during the training. When adding a new refinement block, we froze the model before it and only train the newly added module to reduce the computational cost and memory consumption. By extending the original pointer with the new pipeline, we achieve an improvement of 1.2 chamfer distance on the MVP benchmark validation set. Thanks for listening. Our implementation will be available on GitHub.
Now it will be Yuanjie's turn. Yuanjie, are you there? To share your method for registration.
Oh, thanks.
Oh.
Hello everyone. This presentation is to introduce the champion method on the point cloud registration challenge. Our team has two members, both from the robotic intelligence and the neural computing group in Nanjing University in China. The title of our method is the hybrid optimization method with unconstrained variables. First, this figure shows the registration problem. Point cloud registration aims to find the transformation to align with corresponding points. The corresponding points are connected by these lines. The transformation is made up of rotation and translation following this equation. We directly construct rotation by rotator direction and angle following Euler's rotation theorem. In our method, the rotator direction v and the angle theta as variables need to be optimized. Similar to rotation matrix, we also construct the translation vector by translated direction and distance following these equations. However, in this problem, dm constrains the max distance of translation. So we are not optimized the d directly on the real name domain. To solve this problem, we adopt a mapping function. A mapping function is to extend the range of d. In this computation, we use sign to build the mapping function following these equations. But any suitable mapping functions can be used in consider of data set. After defining the variables, we propose optimization of objective, the hybrid loss. The hybrid loss consists of local CD loss and project CD loss. Those losses are deriving from the transfer distance. The local CD loss limits the number of corresponding points by alpha to improve the tolerance for outlier points, while the local CD loss only pays attention to the local alignment. The project CD loss focuses on the global registration by protecting points to a certain plane. Then we introduce the strategy of optimization and implementations. To overcome the local minimum, we randomly initialize multiple groups about variables. These variables are optimized at the same time. Finally, we took the final result with the smallest local CD loss. We implement our math using PyTorch, and the optimization process is calculated on GPU. The cost of inference took 3 to 10 seconds for one example. In this table, we demonstrate the top 5 results about competitors. The rotated arrow is roughly closed in the top 3 teams. However, our translation arrow has almost decreased 30% over the second team, and the mean square arrow is also nearly 10% less than the second method. Last but not least, we summarize our method with advantages and disadvantages. Considering the advantages, our method is unsupervised and achieves high accuracy to align the pair of cloud points. Our method has strong generalizations, which is programmable and flexibility to fit the data. Meanwhile, it has a good interpretability learning-based method with deep learning. The advantages we think is not real-time, which limits the scope of applications, but we believe it will be solved in the future. Thanks for your listening.
Okay, congratulations and thank you again. If we have questions, maybe we can discuss offline. Now let me save time for Wutong. Thank you.
Okay, thank you, Liang, for the summarization, and thanks all the teams for their sharing. Let's move on to the second part, which is the Forgery Net Challenge. We're honored to have Professor Shen here to give an overview of the challenge. So, Professor, please take over, and the floor is yours.
Okay, thanks, Tom. Sorry. Okay. Okay. And thanks. And I'm here briefly introduce the Forgery Net Challenge. And at first, sorry, I found something wrong with my PowerPoint. Okay, I guess you can hear the screen. Hear me and watch the screen. So the rapid progress of photorealistic synthesis has reached at a critical point where the boundaries between real and fake images start to blur. So it's very important to have a benchmarking and advancing the forgery analysis techniques. Okay, but current data set have almost a saturated performance because they have limited skills, limited diversities, and most of them only have binary labels. But how about our Forgery Net? It is a new mega scale data set with comprehensive annotations and tasks. And so the raw data from our Forgery Net were collected from 4 large scale open data sets like them. And it have diversified dimensions, for example, angles, expressions, identity, lighting conditions, different scenarios, and etc. And we have various forgery approaches. I guess most previous methods only have 4 or 8 forgery approaches, and we have 15, including phase transfer, phase editing, phase reenactment, and phase swap. And include our result, the statistics, we have around 3 million still images, and we have 200,000 video clips. And moreover, what's different, we have diverse rerunning processes as opposed to processing. For example, we have 36 misperturbations, such as optical distortions, noises, blurs, compressions, etc., so that we can generate various damage to the data, so that fools the forgery detection methods. And we have comprehensive annotations, and we have the different tasks. For example, we have forgery image analysis, forgery video analysis, and we also have spatial localization in images and the temporal localization in videos. And in our Forgery Net Challenge 1.0, we have 3 tracks. And the track 1 is forgery image analysis, and the second one is forgery video analysis, and the third one is forgery video temporal localization. And the setting here, we invited participants submit their algorithm, and then training their algorithm on the public dataset, and finally evaluate their performance on our private datasets, and we got our final winners. And here's the policy. Okay, so due to time limitation, I will just omit this page. And according to our statistics, we the baselines reported in our Forgery Net paper, and the total performance from our this challenge, we can find that the performance have amazing gains from the participants. And here is what we want to see, we want to find in our challenge. Okay. And here is some brief summary. We have 2.5 months from data release to the deadline, and we have 178 teams registered to the challenge. And then we have 76 teams to the public test set and 10 to the private test set. And finally, we got 3 submitted technical reports, so that we have 3 winners in some case. Okay, here's the final winner stage. And congratulations, Safety and Security Technology Group, DD. You win the 3rd place as a track 3. And we also congratulations to State Grid Intelligence Technology. You win the 2nd place and also at the track 3. But here we have a big congratulations to the Department of Computer Vision Technology, Baidu. They won all the 1st places at the track 1, 2, and 3. And our talk, the winner talk, also came from the Baidu by Zhou Zhaofan, the senior research engineer from Baidu and Beihang University. Okay, here enjoy the talk. Zhaofan.
Okay, can you hear me?
Yeah.
Okay, okay.
I will stop sharing.
Okay, wait a minute. Okay, can you hear my screen? Hello? My screen can be seen?
Yes, yes.
Okay.
Perfect.
Okay. Hello everyone. I'm Zhou Zhaofan from Baidu VIS. I'm very happy to share our Forgery net competition work on behalf of my team members. Thanks very much for the organizer for hosting this Forgery face detection competition, which will further improve the public dataset of deepfake and vigorously promoted the integration and the development of deepfake detection technology. And I'll introduce our members and Guo Zhizhi, Jiang Shan, Sun Chris, and Zhang Guosheng, Wang Keyao, Yue Haixiao, and Hong Zhibing. Okay, I'll start our repetition. Okay, at present, deepfake detection technology has made great progress in academia, but is not satisfactory in industrial application. We have summarized several challenges in industrial application. 1, complicated real-world data. Most of the research we do today is based on public forged dataset. Deeply forged public datasets are often quite different from real-world dataset. Look at this. Okay. Real-world data may undergo compression and blurring and other image and processing operation during propagation. And these operations destroy the distribution of image to a certain extent. We need to consider this as much as possible when training the model. 2, a low robust model. Many current deepfake detection models can achieve good results in a certain generation of data. But when this generation method challenge, such as hyperparameter and generation methods, many deepfake detection methods will often fail. With this in mind, we need to further enhance the robustness and the generalization of the model in principle. And 3, too much ignorance of some fine-grained information. Many today's deepfake detection methods still regard the task as a true or multi-classification task, and the feature space lacks the necessary supervision, and which results in the learned feature not being orderly enough. And last, time cost. High-speed deepfake detection is very strong demand. We need to strike a balance between the performance and the time consuming, and adding too many complex modules is often contrary to actual needs. So we need to work hard to improve the performance of the model under a certain time consuming constraints. Okay, and And I will introduce the overall pipeline of process of on-chain on track 1, 2, 3. First of all, in order to shorten the pipeline time as much as possible, we put the entire image into the model for multi-class model training. The process of face detection is abandoned, and a large amount of data augmentation, the gas, is added to the training data to simulate the data distribution in reality. So that the distribution of the training data is disturbed to different degree, and the model is prompted to learn a more robust Forgery feature. And during the training, we use the two-stage training. First, we use the global patch-wise consistency structure to conduct a 16-way training. Look at this, and the model obtained at this time, we will be used as a pre-training model for the next stage of training. In the second stage of training, we proposed a dynamic feature queue training method. It adds a auxiliary branch to prompt the model to find a better feature distribution in the feature space. In the end, the image classification model we get and would be used for track 1, 2, 3. For track 1, we directly classify each picture to get the prediction score of each picture. For track 2 and 3, we directly deframe. First, we deframe the video, verify some frames according to a certain sampling frequency, and then combine this result to output the secondary classification result of the video, and according to a certain strategy. Okay. First, the date. Augmentation helps to fight overfitting and improve the performance of deep neural network for computer vision tasks, such as classification, segmentation, and object detection. Augmentation optimized for maximum speed and performance. And under the hood, the library used highly optimized function from OpenCV and NumPy for data processing. The interchange time is shortened, and the augmentations that demonstrate the best performance in most cases. And it supports more than 60 different image augmentation. We use it such as channel dropout and color JIT and FDA and so on. It helps us much. Okay. In terms of structure, we use the constant branch computer the pair-wise similarity score of overall possible pair of local batch in an image and predict 4D consistency value. Give a pre-processed video as input and fed it into the backbone and extract the source feature and for each patch we compared it against with the rest to measure their feature similarity and obtain a 2D consistency map and to to estimate their fixed score. Okay. Inspired by this idea, we applied the face pair-wise consistency to the analysis of the entire image, not just the face pair. We proposed a method called global patch-wise consistency, and we consider that the proportions of the face size in the whole picture has a relatively large fluctuation. So we use the output features of 4 blocks of the ResNest 50 to enhance the ability of the model. Take block 1 as an example. The feature will be batched matrix multiplication, and after 1.1 convolution, and it concat for comprehensive decision making. And this structure divides the feature into multiple patches in different semantic layer. We believe that this is kind of inconsistency among the patch in the partially forged picture, and this inconsistency has a certain rule that can be learned by the model. So different feature from the backbone's multi-stage are computed the pairwise similarity score of all possible pair of local patches. The similarity score would be used to do a 16-way classification. Okay. The second stage of training, we set up a dynamic queue for the forgery feature. We set this queue to sufficient first in and first out queue of about 30,000. This queue will be initiated with normalized random feature. And during the train, we calculate the cosine similarity between the feature in the batch and the queue feature. And the feature whose similarity is lower than similarity threshold and the threshold will be pushed into the queue. And that is to say, the queue store all the difficult negative samples in our training history. But how to calculate the loss? We choose the one. Look at this, and the second picture. We choose the one with the highest similarity pair and narrow their distance through cross entropy loss. And the pair with the closest feature distance is brought closer, and to form multiple cluster, and this and this, and multiple cluster. A sufficiently long queue can help us to solve the catastrophic and fairly many hard samples. And we also set a learnable positive sample center feature and draw all positive sample closer to this feature, which will make the positive sample feature sufficiently clustered in the feature space. Okay. And the train detail, we normalized all image and frame with mean and standard deviation and 0.5 and resize them to 224. And we also used more data augmentation and over 37, including such as JPEG compression and Gaussian blur and color jitter, and to mimic distortions caused by compression and packet loss during transmission, and to improve the generation of the developed model. And for data augmentation and 99% probability random probability random to select 1 to 5 perturbation from some set of these methods and applied it into the input image. And also we adopt the synchronized atom training to A100 GPU, and a mini batch involved 128 image per GPU. and the ratio of the real to fake is each in each mini batch is 1:1. Okay, for video track, track 2 and track 3. For video track, video are disassembled into frames. We uniform the sample 16 frames of each video so that while balancing time consuming and precision, at least one fake frame can be sampled with greatest probability. We can get the fake probability of each frame by classification model inference. We set a threshold 0.5 to judge the real or fake of the frame. That is 0, 3, 6. To judge the real of the frames and use the average score of all fake frame as the video fraud probability. If there are no fake frames in the video, the average score of all frames would be regarded as the video fraud probability. And for example, if the fake score is larger than 0.5, the frame image is predicted fake. And contrary, if the fake score is smaller smaller than 0.5, the frame image is predicted real. And the fusion process is different in track 2 and track 3. In track 2, the result of 60 frames are fused to get the result of each video. Specifically, if any frame is predicted fake in 16 frame, the video is predicted fake as well, and the fake score is average to all the frame and that are predicted fake. And on the contrary, if all the 16 frames are predicted real and the video is predicted real and the fake score is the average of all the frames. Look at this. This is our solution, and in our private test, it could be seen the. Okay.
Sorry to interrupt. A kind reminder that the section time is almost up. There's only 2 minutes left, so you can speak up.
Okay. The more frames extract from the video and the AOC is higher, and we also tried other model and combined with Nest's 15 with X3D, and it gets the highest AOC. But we consider the time consuming, and we finally select the single model with Nest 50. Okay. And the track solution, and for forgery video temporal localization, if the nth frame is fake and the strat of the video is k, and the fake segment is n minor k2 to n add k2. For example, the strat is 2 in this case, and the 0 and the 6th frame are, and the 6th frame is extract, and the result of the first frame are the same with the 0th frame, while the 5th to 7th frame are the same as the 6th frame. Okay. And this is our track 3 solution, and the conclusion is the same as to the track 2. Okay. The higher number frame extracted from video, and the AP and the AR, and it is higher. Okay. Okay. That's all. Thank you.
Thank you. Thanks, Prof. Shen, for the summarization, and thanks all the speakers for sharing their solutions. So let's move on to the next part. Our next speaker is Professor Angela Dai. Hi, Angela. I'll give a short introduction of Angela. She is currently an assistant professor at Technical University of Munich, leading the 3D and understanding group. She's done amazing work on understanding how the 3D world around us can be modeled and semantically understood. Her research has been recognized through a DDB Junior Research Group Award and ECM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention, as well as a Stanford Graduate Fellowship. She's also the creator of the ScanNet dataset, which is really a big contribution to the area of 3D scene understanding and has greatly promoted works in both research and industrial applications. So it's great pleasure to have you here, Angela. So please take over and show us some latest works of your group.
Hi, thanks a lot for having me here. Let me share my screen. Okay, so today I'd like to talk about some of the stuff that connects a bit more to the understanding humans side of this workshop. So I'm going to speak about learning to optimize for non-rigid reconstruction and tracking. So originally I started my research career doing real-time 3D reconstruction. So this is a video that you can see of a live reconstruction from a Kinect style kind of sensor that's being shown being globally optimized. So the entire scene is actually moving with respect to the camera pose updates here. And this actually is a fairly robust system in this kind of static indoor scene scenario. But of course, you know, most scenes that we encounter, and particularly those that are relevant to understanding the human world around us, are not just static. We want to be able to understand actually how things move and deform, especially because people are a large component of actually non-rigid deforming surfaces. So, and there was the seminal work of dynamic fusion by Richard Newcomb et al. And these guys proposed a non-rigid reconstruction pipeline from RGBD that is able to simultaneously reconstruct and track in real time. And so this inspired a lot of research here in this dynamic domain. And they have a kind of non-rigid reconstruction pipeline that looks like this. So here we have an input depth frame, and we can extract the depth from the current warped model that's being built. For instance, like with marching cubes or something like this, we align the input frame with the extracted frame. You can use something like dense non-rigid ICP for the correspondence finding and the optimization there, and use this optimized deformation in order to actually integrate the RGBD data into the model, and then you iterate, go to the next frame, and compute this optimization again. So we want to take a look at this kind of non-rigid reconstruction pipeline and see whether we can reformulate this actually to become a differentiable pipeline, so that we can actually learn through some of these areas where we're currently handcrafting some of this design, in particular the correspondence finding and optimization here. So we want to be able to actually learn correspondence prediction as well as correspondence weights in end-to-end fashion, so that the correspondences and their weights are actually being informed by this end goal task of non-rigid tracking and reconstruction. So this is kind of like inspired by robust optimization. So we have basically the ability to predict correspondences and to predict the weights of how important these correspondences actually are for the non-rigid tracking. So And then of course we can use the same kind of deformation that's been solved for in order to actually integrate these observations from depth sensors into a canonical volume and represent actually the surface of the deforming object. So here we want to be able to leverage actually this gradient flow all the way back through the pipeline so that we don't need to rely on specifying how correspondences exactly are being found, but actually we can actually learn what are the best correspondences for our non-rigid tracking laws. So from the beginning, we have here a pair of source and target RGBD frames that you can see, and we also have foreground mask information of the object that we want to track here. And then we go and predict correspondences from source to target, as well as per correspondence important weights, so that we can deal with outlier observations here. So here you can see a visualization of the source and the target. We have predicted correspondences being visualized here in yellow. And then we also predict the weights per correspondence so as to identify outliers versus inliers for the actual optimization. So we use all of these correspondences as a data term in an as rigid as possible non-rigid optimization. So like state-of-the-art non-rigid reconstruction approaches, we have a deformation graph that's basically defined over the source frame, where the graph nodes are sampled uniformly over the source foreground object, and we can have node connectivity by geodesic distances. So all of this is being used in terms of the final optimization here. So we want to estimate the global translation and local rotation for every node in the deformation graph, and that defines the source to target motion. We can get the dense deformation from this graph by basically interpolating the node motions. So here you can see the estimation of the translation and rotations here for all of the nodes. And finally, we have this loss formulation to encourage the estimated deformation to actually close to the ground truth. And that's informing the gradient flow through the differentiable solvers so that we can actually better inform the correspondence prediction and correspondence weighting. So here we have a more concrete kind of visualization of this pipeline. Here we have the source and the target RGBD frames being visualized, and we want to estimate a dense correspondence map. This is being estimated with a neural network, as well as the correspondence weights for each of these correspondences. So these are together with the graph defined over the source RGBD frame. We have the correspondences and their weights input into the differentiable solver. So this basically computes the graph motion. And we can optimize it end to end with losses on the final alignment on the graph, each graph translation, on the warping, so that basically source actually warps to target. And we also have an intermediate loss on the estimated correspondence maps here. So here we can see an ablation study of our different loss formulations. This is on the deep deform data set. And so each of these losses, the C for correspondence, G for graph, and W for warp, are continually helping in terms of the accuracy in the non-rigid tracking. We also have an interesting experiment here in terms of the correspondence weighting. So here you have this loss in terms of the correspondence weights, whether this is being estimated in a supervised fashion. So we aim to supervise the weights of inliers and outliers based on our ground truth that's known at train time, or we allow this to actually be self-supervised and estimated just based on what's the best performance with respect to the actual non-rigid tracking loss formulation. So actually, if we allow this to be self-supervised, we can learn more informative weights in terms of the correspondences to achieve a bit better in terms of the non-rigid tracking. So we can also compare to state of the art on deep deform again. So this is in comparison to approaches like dynamic fusion, volume deform, and deep deform, which deep deform also is leveraging learned correspondences, but they're predicting sparse correspondences as heat maps, which is relatively inefficient. So actually, this approach that we have here performs better geometrically and is also about 85 times faster, since we only need one forward pass in order to predict all of the correspondences, as opposed to predicting heat maps for every correspondence. So here you can see some qualitative results also in comparison with deep deform, which is leveraging learned sparse correspondences, but the computational cost here is limiting it from actually close to real-time performance. We also have some comparisons with state-of-the-art in terms of dynamic fusion and mono FEV in terms of our tracking and reconstruction here. So we can get a fairly nice kind of tracking. And this is a kind of nice formulation here where we can now actually differentiably optimize through the non-rigid tracking part of this pipeline, because now we actually can learn correspondences and learn their correspondence weights in a robust optimization kind of fashion in order to get better tracking performance. But the shape and reconstruction is still the same kind of pipeline as before. So what about also optimizing for shape as well as the tracking? So this is another work mainly by Aljaž, where we take basically a sequence of depth observations, and we want to perform global optimization of the whole sequence in order to get a globally consistent non-rigid reconstruction here. So here the input you would see on the left, as well as the reconstruction and tracking, as well as the optimized deformation graph that are both being computed here. So here we have basically a sequence of some kind of non-rigidly moving object that's being recorded by a set of commodity depth sensors. And so each of these frames here are represented as SDF grids. So we can go through this sequence of frames and encode their SDF grids just with 3D convolutions here in the encoder. And we want to be able to estimate this neural deformation graph that we have here. So the graph embedding is being characterized by the positions of the graph nodes, the rotations of the graph nodes, and their importance weights, the influence with respect to other nodes, which you can see visualized here. And we also have some global parameters for over the entire sequence. The affinity matrix and the distances are for graph regularization, and the radii are denoting the actual size of influence of each of the nodes. So basically, affinity is describing which nodes affect each other. And the distance matrix here is basically the average node to node distance distances. So we're optimizing over these ones such that with the affinity, basically these weights applied to the node-to-node distances should remain close to average node-to-node distances. So that's aiming to preserve edge length. And we want basically the weights applied to the distances should be relatively small. So we want to have closer node connections. So now we can actually optimize this formulation over the entire sequence. So such that actually we want to be able to fit this kind of deformation graph that it characterizes all of the frames that we've seen. So this is for the tracking side. And now we also want to characterize the surface here. Basically, every node is also associated with a local MLP that is going to estimate local surface regions. So the full surface reconstruction is basically an SDF that's created by interpolating the SDFs from each local MLP and using the node influence weights and the node transformations to the current frame in order to compose them all together. So we can now optimize basically over the SDF reconstruction as well over the full sequence. And so the final optimization here is having losses on graph coverage so that the deformation graph should actually cover all of the observed object surfaces, that the graph nodes should actually stay within all of the observed surfaces. The affinity consistency that I mentioned before in terms of preserving edge lengths and preferring close connections here, as well as a sparse connectivity on the graph, and L1 reconstruction loss on the reconstructed SDFs. So that gives us the reconstruction as well as the tracking that's visualized here as dense correspondences over each of these frames, where the colors are indicating basically tracking over these frames. So let's take a look at some results on real data. So here we have a real data capture setup that has 4 connectors. They're all hardware synced, and we've calibrated them with OpenCV and filtered out basically the floor regions of the capture. So here you can see some example result sequences where we have the reconstructions and the deformation graphs that are optimized for. And so this global optimization actually helps characterize these kind of relatively large, fast movements over time. So in comparison to multi-view dynamic fusion, you can see that we can, well, the multi-view dynamic fusion will get some high frequency details, but it will struggle to track these like larger, faster motions, and it cannot really recover nicely from wrong tracking in this kind of scenarios. So we also have some analysis on synthetic data on this deforming things 4D data set. So here to emulate the real world kind of scenario, we have 4 rendered depth views for every frame of a synthetic animation here. Here you can see again the reconstructions and their deformation graphs. So here there's a comparison to multi-view dynamic fusion as well as SIF and LDIF, which are learned approaches to estimate geometry and end up with some natural kind of consistency, but it's producing sort of somewhat less accurate geometry, and the tracking is also struggling because there's not any explicit optimization here in terms of the actual tracking. So our approach can actually more nicely handle these kinds of large deformations while still maintaining a complete kind of geometric reconstruction here. So this is like a general approach that can also apply to other movements besides human movements. And here you can see again these kind of like big fast motions. Since we're actually globally optimizing over the whole sequence, we can capture these in a nice way. So here this is like a global optimization kind of approach. But if we take a look at like state of the art in terms of human modeling, reconstruction, and tracking in the human domain, what we see are parametric models like Simple that have been built with significant efforts in terms of data collection and analysis in order to actually construct this parametric model that can be basically optimized over in terms of the main modes of human shape deformations. But of course, this is not something that's easy to construct now for every kind of specific domain. In this case, basically Simple applies very well, of course, to unclothed humans. But you know, we'd like to be able to actually construct something similar to this in terms of parametric modeling, but we want to be able to learn the construction of the parametric model so that we don't have to spend the manual efforts to curate and align together everything in terms of the data set to build such a parametric model. So here, for instance, you can see like the Simple model is on the clothes, so we cannot really easily capture any of these details in terms of clothing or hair or all of these other kind of aspects that you usually have in terms of reconstructing and tracking people. So we propose a neural parametric model approach to this, where we want to be able to disentangle the 4D dynamics of a deforming shape into two latent space representations representing basically the shape and the pose. So here we have a visualization in terms of the learned shape space, the learned pose space. We represent these basically as implicit shape and pose spaces with multi-layer perceptrons to learn the spaces here. So when we learn these kinds of shape and pose spaces, that means that we can now actually do test time optimization over the learned spaces to fit to any new observations. So for instance, to the depth sequence that we see here, we can then fit the shape as well as the pose space codes in order to then track and reconstruct this sequence. And so this is actually very similar to the fitting of a traditional kind of parametric model like Simple. So let's take a look at the optimization here. And so when we want to learn the disentangled shape and pose representations, we basically are requiring that in the data set of these deforming shapes, we want each shape identity to be seen in a canonical pose. For people, this is going to be like the T-pose. And each shape identity should be having several posed or deformed instances with dense surface correspondences to the canonical shape, but they don't need to be shared correspondences with each other in terms of the data set here. So that's all that we need in order to be able to actually learn these disentangled shape and pose representations here. So in terms of the shape and the pose, we'll take a look first at the shape here. So this is a latent shape space now that's an autodecoder being learned and conditioned basically on the shape code S. And we want to be able to map query points X in 3D space into its SDF value. So here you can see like the point X and the shape MLP should actually learn the distance to the surface here. So now we have the pose space, which is conditioned on both the shape code as well as pose code, since the poses are not going to be canonical independent of shapes. So we actually have the conditioning on both the shape code and the pose code. And so this learns the mapping from a point X in 3D space again to it's from the canonical location to the corresponding location in the space of the deformed pose here. So this is basically learning these deltas from where it would be originally in canonical space to now in this deformed space. So now we've learned the shape and pose spaces. So now we can actually fit a neural parametric model to an input sequence. Here we have n frames that are being seen. And we know it's the same shape, so we can optimize for one shape code as well as n pose codes for each frame. And we want to optimize such that these are best explaining the input observations here. So here we can optimize this basically such that the shape and its poses are being reconstructed such that they map or they match the input depth of observations, and we also have some regularization in the temporal domain. So that allows us to jointly optimize for the shape and pose codes. And so then we can actually perform a reconstruction here where actually we only need to actually reconstruct the canonical shape once and in the shape space. And then we can actually deform it through all of the frames by deforming it from the pose codes here. So here, this one with the shape, we can get out basically by querying a bunch of locations and running margin cubes to get a surface reconstruction. And then we can take the pose codes along with the shape and query the deformation vector for the vertices in this canonical shape here. So this vertex will then map to the deformed positions, and we can actually just deform this mesh along through the rest of the sequence here. So this, of course, goes the same for all of the pose codes in the sequence. And that gives us the reconstruction result here. So here we have a couple of qualitative results on real data sequences. So this is here on the CAPE data set in comparison to basically simple fitting using OpenPose in order to figure out basically key point locations in order to get the initial fitting here, as well as IPNet, which is optimizing for two surfaces to represent a person, where the inner surface has correspondence to simple and the outer surface will characterize any kind of deformations corresponding to like clothing and stuff like this. And you can see the ground truth on the right-hand side. So here, because we are actually optimizing at test time in order to fit to the actual input sequence that you see, we can get a finer scale detail in terms of things like clothing boundaries. And we can also maintain a better consistency in these kinds of big movements here from the arms. So here again, you can see in terms of the shirt boundary that's being estimated here. And this is because we have this nice kind of latent space disentanglement that allows us to fit more accurately to what we see now in a new frame of a new person and different movements. So here, there's some results on synthetic data. This is from the Deforming Things 4D data set again. And this is also in comparison to simple fitting based on OpenPose information here. And so here, we also have single depth frames being seen, and this is what you have on the left-hand side, and what we are using our model to optimize for at test time to fit these kinds of frames. And that allows us actually to get these nice big motions while actually maintaining a fair amount of local detail in the sequence here. We also have a comparison here with occupancy flow, which is also learning a 4D implicit representation, although it struggles a bit with longer sequences and on also the finer geometric details here. So we have this nice kind of optimization that actually allows us to fit even better to the input depth sequence. So we've also seen a bunch of these results here on people, but this is a general kind of approach towards learning a parametric model. And so we can also do the same. This is on hands on the mono data set. So this is input depth sequences that we see from the mono model. And our approach can also be learned to fit to these kinds of deformations from hand movements as well. And that's not requiring any other information other than having a data set of hands where we have a set of canonically posed hands, and each of their hand identities have some deformation sequences. So we can also take a look at the space that we learn in terms of both shape and pose here, but with basically latent space and interpolation. So here you can see interpolation through the shape space. And here an interpolation through the pose space with a fixed shape identity. So of course, we can also do things like retargeting by remapping shape or pose codes here. So here we have a shape source, and we want to remap the pose codes from a different sequence to this shape. And so here you can see the remapped movements from the pose source now onto this shape source. And for another sequence here, we have the movements from the pose source. We use these pose codes to then basically reanimate the shape source here that you have of this woman. So with that, we have basically these neural parametric models that we can now use to learn parametric models over a particular domain, like clothed humans or hands. And so I just want to point out a couple of cool things in terms of what's next, because of course there's a lot of interesting possibilities here. So one natural thing to do, of course, is to take a consideration in terms of modeling color, texture, and lighting in order to also be able to better handle RGB inputs, as we've been generally considering the space of commodity depth sensor inputs. But of course, you know, like RGB video cameras are far more widely available, and also in terms of data. So in order to actually model the color and the textures, there is an interesting consideration. And of course, there's also been a bunch of work now that's been inspired by NERF that is for novel view synthesis, of course, but is having an interesting formulation here that is effectively capturing the image formation within some kind of observed sequence. So that's kind of interesting in terms of potential extension to actually learning how to also incorporate other aspects like colors and textures into these models. And of course, since I'm also operating a lot in terms of the 3D scene kind of scenario, which we didn't talk about too much today, but the human interactions actually in 3D scenes, especially for indoor 3D scenes, which have been constructed for the sake of human interactions, are super interesting. So this is also recent work, not ours, but is pretty cool in terms of basically tracking a person as they're going through an environment. And I think there's like a lot more possibilities here in terms of also finer scale interactions and really simultaneously understanding actually what's the human behavior and motion, as well as better understanding the different objects and their configurations in the environment, which I think is super cool. And of course, we need to be able to effectively track and reconstruct the people, as well as the static environments in these kinds of scenarios. So with that, I would like to conclude and thank you again for having me, and I'm happy to answer any questions if you have them.
Thank you. Thank you very much. It's very exciting works that you have presented. And we got a few questions in the chat box. So the first one is, if simple with depth may serve as a better baseline than simple in the experiments in the last work.
Mm-hmm. Okay, yeah, so with the neural parametric models, I think, so simple plus simple D is probably a better baseline than simple itself, but the IPNet is actually a bit more of a sophisticated model than simple D, because it's basically also fitting the corresponded simple inner surface with the outer deformations there. So I think we wanted to consider the traditional parametric approach, which is simple, and then also a state-of-the-art learned approach, in this case actually IPNet rather than simple D.
Okay, thank you. So the next question is, would you consider fitting the simple to the output mesh to obtain smooth result? A good idea.
I mean, I think there's still interesting aspects to leveraging, of course, like simple. I think this is mostly because we actually do test time optimization to fit to real world kind of depth maps. You do see a bit of this noise here, and this is probably because our pose space is a bit too flexible. So we're not really we have too much capacity to represent different kind of deformations in clothing, and you end up with a bit of bumpiness in terms of the reconstructions there. So definitely, I think there's something to improve. I would probably go more for the actual pose representation itself. I mean, mostly because along these lines, we're still aiming to be fairly general and don't want to necessarily be attached to the human domain by modeling directly off of simple. On the other hand, of course, I think this kind of hybrid approach where you have something like simple or some other kind of basis function that is providing you some coarse representation of the geometry of the tracking is still very interesting, especially for these domains where you can rely on having the domain specific knowledge in order to just directly optimize for these sequences.
Okay, thank you. And another question is, I would like to know whether there is a general method to build neural deformation graphs for different instances, or the graph is predefined for each instance.
So I'm not sure I totally got the question, but I'll try to answer that. The neural deformation graph is learned per sequence. So basically, it's predefined in the sense of we have a max number of graph nodes, which I think is 100. I might be wrong, but it's around 100. And that's basically being optimized then that it fits to the particular sequence. So I'm not entirely sure what's being meant by predefined. Like basically for new instances, they can be learned specifically for the new sequences in order to reconstruct and track those. But in terms of like stuff that we define is basically just the max number of nodes there.
Yeah, that's true. And the last question, what do you think is the biggest reason for simple to fail in the point cloud input?
So I'm not sure if you're referring to a specific sequence, but in general, like simple fitting is particularly, I mean, it's like an optimization, right? The basin of convergence is not that large. So you have to have a good initialization for simple fitting to work well. So that's why we actually have the open posts along with simple, so that we can actually tie the simple fitting such that it tries to hit this basin of convergence. But if it starts too far away, like if you have basically strong movements or slightly occluded kind of regions in the body, then you will end up with basically some estimate that starts too far away to actually converge well to the geometry that's actually being seen there.
Yes, yes. That's very reasonable. So thank you. Thank you for your great talk, and thanks for the questions, and thanks for the answers. So thanks for joining us. Bye-bye.
Thanks for having me.
So here we comes to the coffee break, and we'll be back in 10 minutes. Hi, welcome back. So for the next section, Zhongwang, also one of the organizers of us, will give a talk on building infrastructure for 3D human recovery. Zhongwang is a first-year PhD student at S-Lab, Nanyang Technological University. His research directions include virtual humans and point clouds. So Zhongwang, please take over and talk.
Sure. Thank you, Wutong, and a very good morning, good afternoon, good evening to our fellow researchers all around the world. Let me share the screen. All right, hope everything works fine. Right, my topic will be building infrastructure for 3D human recovery. I'm going to share a little bit about what we are doing, and probably some of them are going to be very helpful to your research. So today's agenda, we started with some preliminaries, most of them are on the human parametric models, as well as some other contexts in the industry that actually drives us to do what we are doing. And the following that will be a code base. Will be a code base sharing. So as I just said, some of our work is really aiming at helping the community to move forward. So one of the effort we are putting in is that we develop a code base that we hope to ease the burden of implementing all the soul tasks yourself, and we can help you with this. And after that, because we know that data is always the bottleneck for data-based research, and we are here to explore some unreasonable effectiveness of data. And here we actually develop a data set, and by playing video games, it's going to be very fun. Right, and last but not least, I'm going to share some of our recent work from the team that's beyond human body modeling, because we are mostly working on simple, but simple does not describe the entirety of the human, because as humans, we also wear clothes, right? So beyond human body, so what we have just done. Right, some preliminaries. As we know that we are living in a world that's full of entertainments, most of them are actually human-centric. By saying human-centric, we are talking about because all the characters, we normally have a storyline, and all the characters in this storyline are humans most of the time. For example, there are movies, there are games, animation, and most recently, there are virtual YouTubers. Maybe some of you are familiar with them. And you can see that the center of the stage is always humans. So modeling human is very important. And we can see below a standard industrial pipeline that modeling human in a standard way will be very expensive, especially there are two stages, modeling and animation. So if we can automate these two stages, you will save a lot of money and also drive the industry forward. So what are the solutions available? First of all, will be surface model. As we know, all the implicit functions are actually fall under this category, and also Paipu. But the biggest problem with surface model is actually it lacks body semantics. That is, we have a very good description of the human body surface. We know the geometry, but we actually it would be very difficult to extract something such as the pose of this person. Then it will make it difficult for us to transfer the pose of an estimated model to some other animated characters. Technically will be key point model. Key point model is probably the mainstream for human pose estimation in the academia at the moment. However, we know that there are also some problems with key point model. That is because if we don't have enough key points, the constraint will be insufficient to to have a complete description of the person's pose. We can see in the green box that on the left side of the green box, we actually have two mannequins. Over there, if we define the joint positions indicated by red dots, we can notice that the body is not actually fully constrained, so we can still rotate the arm along the arm's own longitudinal axis. And so the description is actually ambiguous. And also, if we look at the right, we have an example over here. because of the lack of proper constraint, the fit of the character actually is quite awkward sometimes. Secondly, there's another limitation of key point model is that we are unable to model things like touch and the interaction with the environment because the key points or the body joints usually the large body joints are inside the body. So we actually need something that's floating on the surface and allow us to interact with the environment. So parametric model actually come to rescue. So you can see over here, the parametric model we are using here is simple and simple X. It consists of a lot of parameters, and by using this low dimensional parameters, we are able to describe the high dimensional human body. We can, because of the parameters have their own explicit meanings, we are able to tell if there are parameters for the shape and also there are parameters for the pose. Together, it allows us to perform reconstruction as well as manipulation at the same time. So maybe you're familiar with this image. The reason for us to choose human parametric model, or we consider human parametric model, is one of the important direction is that we find that it's a compact representation. As I just mentioned, we can use only, for example, we can use only 72 pose parameters and 10 shape parameters to describe to give a complete description of the human body. And also, because of the compactness, it will actually allow us to run this network very fast. And because of the completeness, we are able to do away with the ambiguities. Another interesting observation is that recent years, the 3D vision has been developing really fast. Some of the reasons are attributed to the hardware advancements. For example, we have Microsoft Azure. Actually, Microsoft Kinect has been around for about 10 years, and the Azure is the latest member of the family, and it is just better than ever. And this actually opens up the opportunities for us to use consumer level RGB cameras. And on the right will be something even more exciting is that Apple has released its flagship iPhones and iPads with LiDAR sensors mounted on them. So this actually indicates Apple's ambitions to develop their AR technology, but also opens up the avenue towards allowing more 3D sensors to be in the market and to advance the development in the relevant fields. Right, so the first exciting progress is that we are building a code base that is all you need. Actually, you will find out why this is not an exaggeration. So let's look at some common challenges we have as a researcher on things like human parametric model or human pose and shape estimation. Is that we have many excellent works in the academia already published, but reproducing them is actually it's a pretty big challenge because many of them have a slightly different environment and we need to set up and we need to align all these hyperparameters just for us to reproduce the works. It is difficult overall. And also what's more frustrating is that because there are many thousands of human-related data sets in the academia, each of the data sets are having some slight convention differences. So for example, dataset A has 21 key points and dataset B has 19 key points, and aligning them are going to be pretty troublesome. Third would be because most of us are more experienced with computer vision, we probably lack the background knowledge on things like mesh and the rendering and texture, but these are essential for human modeling, especially with parametric models such as simple. So our code base actually comes to rescue. Yeah, the first it would be it makes reproducing the existing code pretty easy. So just a press of button away, as we put it. This is true because we actually employ a config system, and our framework will build the model for you according to the config. I'm going to share a little bit more details later. And also we present and propose a human data convention that is to align all the supported data sets. So for all the data sets we support, we provide preprocessors to convert all the dataset raw information into our human data convention. Then all the pipelines behind that will be just using human data straight away. So there will be zero misalignment. And we have a rich collection of tools, and some of them are implemented by ourselves. They are designed to lower the entry barrier. So things like rendering and visualization will be a breeze for you. So everything is settled and handled by the visualization tools we provided. So this is the overall architecture. Probably because of the time constraint, I probably don't have the time to go into details. However, just to point out a few things is that we have some important third-party dependencies. First will be SimpleX, but instead of using SimpleX directly, we actually developed better wrappers around it. So we're going to give the existing SimpleX a little bit more capabilities for us to better model Simple and SimpleX. And it will be PyTorch, basically the foundation of everything, so you can continue to use your familiar interface, and our code base will be compatible with PyTorch completely. And very interestingly, we actually include PyTorch 3D in the code base. And this is because we find out that differentiable rendering, which is supported by PyTorch 3D, is going to be it actually opens up a lot of space for imagination. And we want to provide the academia the newest toolings we have. So we actually include PyTorch 3D, and PyTorch 3D is replacing other amazing visualization tools such as Open3D in our code base. Okay, so what are the supported algorithms? We here present 5 classic, and some of them are the latest SOTAs in the academia. And this is only for the first release. So after that, we're going to introduce even more algorithms. So the code base will support more and more algorithms in the coming year. So first of all, we have Simplify and the SimplifyX. These are the most classic registration-based methods, and you may even need it for data annotation. Then we have HMR, as we know that HMR is one of the early endeavor in introducing deep learning into human pose and shape estimation. After that, we have Spin. Basically, it's quite similar to HMR in terms of the architecture, but it has additional online registration module, making it very effective in the case that because we don't have sufficient simple annotation. And after that, we have Vibe. Vibe is one of the first deep learning-based method that leverages temporal information. Basically, it takes in videos instead of single images. And the last but not the least, we have Hybrid. It's also a deep learning-based method, but it actually introduces a novel formulation that significantly boosts the performance of the model. So so this will be the 5 algorithms we support in the first release. So how do we actually design the framework that makes reproducing works easy? Is that we try to perform some high-level abstractions to ensure the scalability of the code base. So as we know that we're going to have more and more methods, how are we keeping the code base manageable? It's by abstraction. For example, we have showed 2 examples here. For the image-based methods, they can be abstracted as all of them having some sort of a backbone and the optional neck probably, and the head, which is providing the regression results. And also, we're going to have modules such as registration. Here, registration may be Simplify or SimplifyX to provide some additional supervision. And also a discriminator. Let's say we are using adversarial training. And for video-based, it's more or less similar to image-based, but the only difference is that we normally have a very long neck that is across the temporal axis that is able to capture the temporal cues. And also we have the backbone, the head, the registration, and the discriminator. So just to show how does the supporter algorithm fit into the modular design, is that for in case of HMR, the backbone is ResNet60, and it has 3 FCs serving as its regressor. It has a post discriminator to help with the training. For spin, it's very similar to HMR, except it does not have a discriminator. Instead, it has a registrant. In this case, a simplified module. And for Vibe, everything is similar. It has also a motion discriminator, but in this case, the temporal encoder is actually elongated, and it covers more frames than just a single one. So this is one of the sample config file you may find in our code base that actually gives back. So how do you use this config file to build your own module? It's very easy. Just define your own backbone, your head, and also as well as a discriminator. So you can. This is example for HMR. So it has a discriminator over here. And there are other things you need to define, such as the body model you use and the losses. With that, the framework will build the model for you. You don't have to write a line of Python code to implement it yourself. So with that, I just introduce you the convenience of reproducing the existing SOTAs. And now I'm going to show you some tools we provide to help you with research. First of all, we provide a series of convention tools. First of them is the camera convention tools. As we know that there are a lot of camera conventions. We have the PyTorch 3D convention, and also the PyRender behind it, more commonly known OpenGL convention, and there are OpenCV, and the same convention also used for Open3D. And there are all types of conventions are supported. Some of them are using left multiplication. Some of them are using right multiplication, and some of them define the extrinsic as word to the camera, and some are defined in the opposite way. So with our tools, you don't have to worry all about this, and the tools will convey it for you automatically. And after that, because we are dealing with a human parametric model most of the time, and joint rotation is one of the essential topic we need to address. So here, our tools support several popular joint, or rather rotation conventions. For example, the most common or the default convention would be axis angle for simple and simple X. And also we provide support such as rotation 60, which is also a very common convention for deep learning based methods. And also here we introduce a new convention called standard joint angles. It is designed to help us with joint constraints, because as we know that axis angle, the 3 values are kind of coupled. You can see on the left, if we change the value of one axis and we change another value, normally there will be coupling effects, and it will be very difficult for us to design some joint constraints. So in the spin or a series of works, normally there are only 4 body constraints applied on the elbows and on the knees. There are no other joint constraints. So however, using our standard joint angles, we actually decouple the 3 rotations. And so we can apply some axis specific joint limitations to them to help us designing a very even more useful full body joint constraints. And as for the key points, we all know that there are a lot of key point conventions. Over here, we introduce a superset of all of them, and we call it human data 1.0. This is part of the human data 1.0, but for the key point part. As you can see, this is really a superset of key points. Can find any key points in any data set to be also existing in the superset. And we visualize the superset on the right. And you can see that all these conventions on the left in bullet points are supported. And each of them we actually implement some mappings from each of them to the human data 1.0. these are some of the examples. On the left will be a COCO dataset. On the top right, 3D-PW, and on the bottom right will be human 3.6M, and all of them has implemented joint mappings to bring their joints to have the correct mapping to the human data v1.0 convention. So everything is aligned, and this will help us develop. This will make the development of the following pipelines after the data loader pretty easy. And also because I just mentioned about we're going to provide preprocessors to preprocess all the data sets into a standard human data convention. So we show here on the left are all the data sets supported in our code base, and our processors will process each of them into a standard human data format. As I just mentioned, it will make the data loading pretty easy, and this will also benefit the development of a universal data augmentation pipeline. Now we come to the visualization parts, and over here we can see here is the visualization of a human 3.6 M data. So we can see the clip here. We are able to show the key points as well as the corresponding 3D key points in a pretty easy to see way. And on the right, you can see we have the three. We can even rotate the 3-dimensional axis. This is also supported. And because we are dealing with human parametric model, and it is quite intuitive to wonder if the visualization of human parametric models are well supported in our dataset. The answer is definitely yes. And you can see here our visualization tools are able to provide a lot of functionalities. On the top left will be the simple overlay, and we are able to separate the body parts. So there will be part segmentation, and also we are able to show the vertices as well as the key points visualized as part of the point clouds. On the bottom left, there will be the depth visualization, and also semantic segmentation, and also part segmentation. But this time, there's no overlay. I want to highlight that all the visualization tools we provide actually supports differentiable rendering. This actually, again, this helps us to develop some novel methods, and you may find this very useful and beneficial to your research. So on behalf of the development team and the adversarial board, I would like to thank you for your support. And if you want to know more and get the latest updates on the release of our code base, please scan this QR code. And don't worry that this QR code will be shown throughout the presentation. You have multiple chances to catch it. And also we welcome all the contributions. This is not a closed door effort. We want to welcome contributions from all over the world from you guys. Okay, the second topic will be exploring the unreasonable effectiveness of data. So as we know that there are two main streams of methods for human pose and shape estimation. On the left will be registration-based, then on the right will be direct regression. The registration-based methods works pretty amazingly. However, the problem is that it takes a lot of time. As you can see over here, if we try to just fit a single frame of simple X, it takes about 2 minutes to do it. However, on the right, the direct regression method will be a lot faster. Normally, it takes less than 1 second. However, as we know that to train a good CNN or rather a deep learning model, we need a lot of data. But collecting a lot of data for simple or for human pose and shape estimation is pretty expensive. As a study done in ICCV 2019, it is shown that the sparse 2D key point annotation is relatively affordable. But when it comes to annotating 3D annotations, especially in the wild, the cost is almost prohibitive. So we address this problem. The answer is we playing video games. So here we present GTA Human. This is our recent effort to simulate and also produce a lot of decent quality data that is in the wild because we are playing video games. The game we use is obviously GTA 5, which is a metropolis with all kinds of people living in it. And because we are collecting the data on the entire map, we are having people essentially in the wild, right? Then if we annotate the data, we are obtaining paired data almost for free. And definitely we are not the first one to use GTA to produce data for various tasks, various vision tasks. However, I need to point out that there are two differences. For example, GTA Human, as to the best of our knowledge, is the first one to generate game playing data and with simple parameters annotated. And also, it is pretty large scale, and I will show some figures later. So to make this possible, we actually employ some cloud-based services to coordinate a really large number of local GUI workers and also GPU cluster workers to make this the scale possible. And also, as I promised, I will show some figures. GTA Human is probably one of the largest data set available, and it has 1.4 million simple annotations, and there are in total 20,000 video clips, and there are slightly above 600 subjects, which is quite competitive. And also because we are sampling from in-game data set of about 60,000 actions, we are able to downsample them and find the most expressive 20,000 and assign each sequence a unique action. This is probably never done before. And here we show some proof for the diversity of the data. As you can see in sub-figure A, we have all kinds of people wearing different clothing and in different body shapes. And in sub-figure B, we have different locations. We have data collected from the city area. We also have the data collected in an indoor area and also in the wild as well, literally in the wild. And also because we have access to the weather system provided by the game, we're able to generate data in different weather conditions. And in sub-figure D, I find it most interesting is that we are able to set the in-game timing. So this will allow us to actually control the lighting conditions. As you can see, the shadow of the statue is actually changing with time. Talking about actions, because we have a very large post database, and the distribution is pretty, the range of the distribution is pretty large. And it's worth noting that the distribution of our GTA human dataset is actually covering entirely the real dataset. So everything exists in the real dataset is likely to be covered by GTA human dataset as well. And here we show some videos, video clip, show some post sequences, and you can see over here that if we visualize the post sequences, it is very expressive. Some of the action even expands across the entire distribution. And some results, because we actually find out that directly more probably training from scratch using our synthetic data would not be a good idea, because there are essentially some domain gap, which is another interesting topic that's worth exploring, but not within our scope at the moment. So we experiment and develop some special schemes. Some of them may be blended training with the real data set, and another alternative would be fine tuning. And we are able to achieve pretty good results. And with more data added in, the result is getting better. And also for just now, it was on single images. And in this table, we show some results with pose with a video. So actually, we have obtained pretty surprising results. So if we compare with a real data set, but that's collected indoor with equal amount of data, we actually is on par with the performance trained on the real data set. And if we're using the full GTA human data set, we are our performance, the model trained has a performance on par with the in-domain training set. That means we compare with a model trained on 3D PW training set. The results are just mind-blowing at the moment we see them. And on the bottom will be some video clips we collect, we sample from the data set. As you can see, some of them are really expressive and interacting with the environment well. And with that, here is on the left will be the homepage to GTA Human, or you can just enter in your browser that gta-human.com. There you can find our homepage. And also again, if you're interested in this data set, please scan the QR code on the right and register. So we are able to send you an email once the data set is released. Okay, I think I'm rushing for time. So for the last part, beyond human body modeling, we need to rush a bit. So as we know that there are a lot of, for example, AR and AR applications that's requiring more than a naked body model, such as simple. So garment reconstruction is without a doubt a very important topic that we need to explore. So today it is my pleasure to present to you one of our latest work, and the first author is Bangzhou Hong. In this work, we essentially this is essentially the first work to reconstruct garments from point cloud sequences, and it will be presented in New Rips this year. So so why are we using point clouds? Because we want to ensure there's no ambiguity of scale, and the point cloud will allow us to achieve this. And it is very important that compared to some existing works, we want our clothing to be separable from the human body mesh. And the third would be interpretability, which is pretty ideal. That is ensured through a shared topology of the same kind of clothing. And also, we want to model a loose garment such as long skirts, and that is pretty difficult, if not impossible, for the existing methods. And we want our method also to capture some dynamics of the clothing, so it appears very realistic. So how does our method compare to existing schemes? So template-free RGB input methods such as PyFu are amazing work, but however, although it can model loose garments, it has pretty bad interpretability and also separability. And for simple plus D, which is also another alternative, it is highly interpretable. However, it cannot model things like a loose garment, but our method is able to achieve them all. So we unfortunately, I don't have the time to go into the technical details, and if you're interested, please find out our paper. And just a brief go through would be, firstly, we have the input point cloud. Then we first reconstruct the garment on in the canonical space. And that we propose a new module called interpolated LBS to transform and to deform the clothing according to the pose. Then we run a post-garment reconstruction, taking into temporal cues to further refine the reconstruction, and then we can see it's pretty close to the ground truth. Here's some more results. As you can see, our reconstruction is pretty robust, and it can handle various poses pretty well. Yeah, with that, I end my presentation, and thank you very much for your attention. Please be sure to scan the QR code and register if you are interested in our code base and the GTA human dataset. Yeah, I would like to answer any questions if you have them.
Thank you. Thank you, Zheng, for the sharing, and it's really great works and both the data and the code base.
Thank you.
So any questions from the audience, feel free to type them in the chat box. So I'll just ask a quick question. You mentioned many supported algorithms, and so I wonder, will methods for simple X, such as expose or frank mocap, be supported?
Yes, definitely. This is within our plan. However, as I just mentioned, in the first release, we are focusing on simple-based methods, so registration-based and deep learning-based. Most of them are for simple at the moment. We're definitely looking at more advanced methods such as expose and the frank vocab that supports simple X that will come in the later release.
Thank you. So any questions from? So if there's no questions, thank Zheng again, and we'll move on to the next part.
Thank you.
We'll probably take a coffee break here so that we can wait for our. Oh, Professor Su is here, so let's go on. Our next speaker is Professor Su, and it's great pleasure for me to introduce him. So Professor Su is currently an assistant professor in the university at UC San Diego. His research focuses on theories and technologies to build autonomous systems that can actively and continuously learn in the physical world, including computer vision, computer graphics, machine learning, generic AI, and robotics. His work, like ShipNet, PointNet series, and GraphCNNs, have significantly impacted the emergence and growth of 3D deep learning, and applications of Su's research include robotics, autonomous driving, VR, AR, and smart manufacturing. So it's great pleasure to have Prof. Su here. So please take over and show us some latest works of the group.
Can you see me my screen? You're able to see my screen? Hello?
Hello? No? We can't see, I think.
Oh, okay. Are you able to see my screen this time?
Yes, yes, perfect.
Okay, thank you very much for the introduction. I'm very honored to be here and present some latest work on my group. This is a talk also I presented in a workshop yesterday, but with a slightly different focus. And the topic I'm presenting today is 3D compositional learning by parts. Okay. Okay. So many of us are here to study computer vision due to the many success of machine learning. And machine learning has been very successful in many applications in the past decades or dozens of decades, or like past a few decades. Okay. We saw that with a lot of data, we're able to achieve image classification.
Jamba Juice!
Okay. We're able to achieve image classification, speech understanding, or 3D shape classifications kind of applications. Wow, right? And that's backed by a lot of data, image data, 3D data, and a lot of data, they have labels. Okay, and having the data and the labels, we actually sometimes have to face the challenge that on the test data distribution, the test data distribution may not be the same as the training data distribution, right? So we have to face the problem of out of distribution generalizability. The world that we are facing is actually combinatorially complex, right? So the data that we use to train may not be exactly the same as when we are tested. And for the children who are playing the Lego games, right? They may have to build certain kind of fictionary object that may not really exist in the world. Somehow they are still able to see the structure, right? To understand the physics and to manipulate the objects, all kinds of the tasks require the ability to deal with and see objects. Okay. And when we are trying to browse, for example, the internet, right, we try to purchase products, we also face a lot of unknown objects. Right? So for the problem of humans or face, later I will also present our work of synthesizing faces, which are also like you may need to generate the fictional objects. Okay, and when you are having to address the case that the objects in the world are combinatorially complex, then a very natural idea is actually compositional learning. Right? This is not something really fancy. It's just what everyone has been experienced from the kids to grown up. Okay. Like for example, a kid may just stay in a room or in his house or her house for for the first few months of his life, and it actually learns some basic skills, just from very limited environment on a small set of problems. And then the fascinating part is they're able to solve complex or diverse tasks by recomposing the basic skills. Okay. This is also how people learn and apply knowledge. Okay, and in terms of the 3D, what are the basic reusable skills? And argue that they are like paths and the path relationships. Here, the examples are the furnitures, but it also applies to like humans or to like faces. Okay, and the assumption is that different shapes share similar parts and part relationships. Like here, the training data, it's a chair. For example, analysis or synthesis tasks. And then the test data are different. Like here, they are kind of, they are the objects very different from chairs. Right? They are like here, the shelves. Okay. Although they have very different global geometry in terms of parts, they are very similar. Like the plates, like the beams, right? And in terms of part relationships, they are also preserved, or they're also transferable across semantic categories. For example, for the bars or the plates, they are often either parallel or orthogonal. Okay, so understanding part is important. And here I just gave some examples like analysis. It helps us to learn from known objects, but like learn segmentation from known objects, but has the ability to segment even unknown objects into meaningful units. And the units are often, even not only their geometry, including their functionality, they're also often shared across the data set. that would actually allow us to reason about the structure and the usage of new objects. And reconstruction. We all know that the task of single image 3D reconstruction is hard. If you want to infer the structure of an object under this kind of like underdetermined case, you need certain kind of prior. If you have global prior, that's fine, but it limits the ability to deal with unknown objects. If we rely on part level prior, it becomes a very natural way to deal with unknown objects. And then last is the controlment, which is what human and face researchers are specifically interested, because when we are trying to like synthesize, especially synthesizing novel shapes, we do want to have very fine-grained ability to control the synthesis process. And then part gives you a local level of tuning, sorry, not turning, tuning in synthesizing 3D shapes and images. Okay, so that gives us 3 technical questions to be covered in this presentation. The first is I'm going to talk about how to segment a 3D point cloud of unknown objects into paths. And the second is how to reconstruct the 3D of unknown objects from a single image, leveraging part level priors. I plan to use half of the time to cover the first 2 problems, because they are 3D and also shows the importance of parts, but are not human or portraits. And then for the last question is, how can we use 3D part information to guide the synthesis of human faces, or portrait images? Let's proceed. The first topic about segmenting a 3D point cloud of unknown objects into paths. Okay, our computer vision conference today actually like a lot of literature in computer vision conferences are about the part level analysis, but most of the works focus on the setup when the training and the test object categories are the same. Like you train on chair data and you test the chair data. Whereas for this work, we're talking about the test data are from a different set of the training data. So this is you can take the test time is a 0-shot segmentation problem. Test time is a 0-shot segmentation problem. Now here we might train on chairs, but test on faucet or on beds. And this work is based upon an ICCV 2020 paper of my group. Okay, so what is the classical pipeline, right? Classical pipeline assumes train test data are the same distribution. So we actually have a lot of lessons of how to do the work well. For example, a very classical pipeline is the fully convolutional architecture that we use convolution to process local regions and extract per point features, right? And then we use up convolution to gradually get high resolution labels for each point. And how to build a network that works really well. And then the popular belief is that, okay, build a very deep network, right? If you build a deep, well, there are a lot of works that are of this style. But the issue is, if you build a very deep network, then the high level, or at least the bottleneck level, will have large receptive field. When it has the large receptive field, it sees the whole object. And then, because you're seeing the global shape, you will face the challenge that test data is different from the training, and the generalizability will be difficult. Especially considering that the neural networks has a lot of behaviors that are hard to predict or control. Like think about the adversarial examples, right? When the data is unknown data to the network, its behavior gets very messy and predictable. Okay. So in the case when the tested data are distribution, this kind of a fully convolutional and the deep neural network has problems. And one of the way to fix the issue is to introduce attention. Attention could help. From our experiments and previous experiments, attention could help. On the other hand, the problem is also not, in theory, it's still there, right? Because you have the attention module. The attention module is usually still a fully convolutional network that will take the whole shape as input and output the attention mask. Now, if the input is the whole shape, it still might experience weird behaviors when it sees an unfamiliar shape. Okay. In practice, we did observe a lot of issues. Okay, and here's an example for comparing different state art or different existing approaches for the zero-shot classic segmentation task. Right, the GSPN, SGPN, WCSEG, and the PATNet here is a method which is fully convolutional approach. They're all kind of a fully convolutional or attention-based approaches. GSPN is, you can think of it as attention-based approach. Okay, these approaches all cannot handle the novel object category so well. And then for our approach, which you can see it's able to handle the novel categories much better. And to say that among the first 4 baseline approaches, in fact, to our experiment, GSPN is pretty good because of the attention mechanism, although it's still not as strong as our approach. Okay, so how did we build a system? The high level idea is we want to be very conservative in increasing the receptive field. Okay, it's like if we think that to face novel shapes, looking at a global shape might be hurting or to cause unpredictable behavior network, we try to constrain the receptive field. And the second thought is for humans, when we try to infer the structure of unfamiliar objects, okay, we somehow have a kind of a complex reasoning process, and the people often isolate regions of interest from the rest and do this kind of reasoning. So here, we also formulate a problem to allow explicitly isolating regions that are not interested to help reasoning. Okay, actually have generalizability. So that's a agglomerative framework that aligns with that's a bottom-up framework that aligns with the agglomerative classroom. Right? The agglomerative classroom, right? People just to try to group, find neighboring pixels with high chance to be grouped together and then group. And we basically formulate this kind of idea by a learning-based framework. The beginning of the system is a super pixel or over-segmentation method. Like we will use certain kind of heuristic or learning-based approach to segment object into small parts. And for each part, they will have very simple geometry and texture, getting homogeneous. And this is a doable for those simple structures. Usually they are not across 2 semantic or functional parts. And then there's a neural network to suggest paths to be merged together. But here we take a grouping-based methodology. So for adjacent paths, there are so many adjacent paths. For every pair, we actually give them score and then ask them to compete. So that basically is forming a high-dimensional softmax loss. Okay, so the one that will win or with the highest chance that should be merged will be picked up, and we will have a verification module. And then we'll try to merge them together, form a big part, and use a second neural network to justify or to check, to verify its purity. By purity, we mean, do we think that the merged units seems to be a reasonable step, or is kind of a very weird shape? If we weird shape, we reject. And then choose the second best candidates from the policy module and verify again. And you see that this is a hypothesis testing procedure, very much similar to how humans reason. right? For humans reason, we also often do this kind of hypothesis testing. We explicitly isolate the part of interest from what's not interest. Okay, so this is an approach that will give us better result. If the proposal passes the verification, okay, so if it's rejected, then find the second best. If it passes the verification, then we'll form a new path. And this new path will be put in a pool, and the original two subpaths to be merged and form new path will be discarded. Okay, and the way we'll repeat this procedure until the algorithm says, okay, all the the verification says there's no other good paths to be merged. Okay, so then the algorithm stops. So here's a summary of the algorithm. First, if you're facing the zero-shot segmentation problem, which I think is a good problem that I suggest, like if you are not only interested in human or face, but interested in generic 3D understanding problem, could try, because this is a challenging and a lot of established philosophy in deep learning or computer vision does not fully apply. Okay, especially the lesson here is controlling the context. It's very important, helps generalizability. And finally, the algorithm I'm just proposing, the cluster-like approach, it's just a very preliminary attempt, right? Because when people form hypotheses and test it, there are a lot of more flexible ways to do it, right? We are kind of just giving a greedy approach. For example, if we made mistakes in merging, then we have no way to backtrack, and there will be a lot of possible ideas to improve it. Okay, that's it for the first work, and for the second work, I'll try to be fast in introducing it. Reconstruct the 3D of unknown objects from a single image, leveraging part prior. Okay, so the task is we want to lift a single image to 3D. Okay, and here this problem, actually the single image to 3D problem is like a lot of people are studying it, but for our work, we are particularly interested in the case of zero shot single image to 3D lifting. Like the training data, sorry, at the inference time, you are facing an unknown character. Like you train on chairs, but test on beds. Okay, so this is a very difficult problem, and using path-based approach to solve it, this is also quite a preliminary work. So we actually take a strong simplification assumptions. Like here, the paths or the 3D structures are simply the assembly of cuboids. But we also have the third work to present, which is on the portrait. And there you'll get a sense that like having a basic part structure, even is using a very coarse way to represent it, is still helpful, because there could be subsequent steps to create fine-grained detailed structures. So yeah, one just to say is like a structure and the decorations, the details, there are two very different things that is okay, in my opinion, to study them separately. Okay. In the single image 3D literature, there are a lot of work, but they mostly focus on the low-level representation differences, like point cloud versus mesh versus implicit function versus like a volume representation. Right. But when it comes to zero shots image reconstruction tasks or this strong transferability setup, what we believe is the low level, kind of believe that the low level representation doesn't seem to be, or through many experiments, low level representation doesn't seem to be the most critical challenge. The most challenging part is even the basic structure is hard. Okay, let alone the details. Okay. So the assumption here to use part is low level local information and the low order information. Like by low order, I mean part-wise, the relationship between a pair of parts, not many parts. Okay. Now, if you decompose the global or high order information to the local and the low order ones, we tend to get an approach that might be more transferable. Okay. But still, it is question of how to design the modules corresponds to the local and the low level information to be transferable. Okay. So here, for the subsequent discussion of this project, we will we will actually study from the perspective of how to build more transferable modules for paths and path relationships. And we show the results of us. Okay. So the data set is from PartNet, which is my 2019 CVPR paper. That we have a lot of 3D objects in categories, and each category has consistent path labels. Okay, like if we say a laptop is made of keyboard and screen, then every laptop is labeled as keyboard and screen. Okay, so the approach is actually very straightforward. You say it's a modularized pipeline. It's very different, but it's also very different from the end-to-end app convolution kind of pipeline. So here, the modules include to detect the paths, get the path masks, and then predict the orientation of each path, and then predict the size of each path, and then predict the pairwise relationships of paths. Okay, you see that this kind of is a very straightforward way, right? It decomposes the big problem into small problems, and each small problem is solved with deep learning. And we hope that for in this way, we're able to study what's the right way to build the modules. Okay. Next, let me show you through results of how to achieve each module in a transferable way. Okay. First, we will detect paths from 2D input. Okay, the input is an image and the output is the path mask. And here we actually try to mask RCN. We try a few, including the most straightforward UNet architecture. Somehow the lesson is masked RCN has much better generalizability than UNet. Okay, which is like here, this result, the training set are chairs, and we're only showing the test chairs here. The test categories here, sorry, the test categories here. Training on chair and test on table and bed. And you see that I would say the result is, when I first saw it, I feel it's performing better than I anticipate. Like the table paths and the bed paths, they are basically segmented out. But if you check the results of a UNet, it's very messy. The reason is probably because Mars RCN is in fact a detection framework that it will first localize the paths and then segment. So this localization step is introducing an isolation effect, right? You are cropping the features and there, cropping the feature of a region. That is helpful for generalizability. And then we have the paths. Just from the image appearance, I would like to predict the 3D rotation of the path. Okay, here we use a neural network to predict the 3D rotation. And there are certain tricky paths for the rotation. Now the biggest challenge comes from the ambiguity in representing the rotation. So for the ground truth for each of the paths, for the 3D path, because we are using the PartNet, which is a 3D data set, we do have the 3D ground truth of the path structure. On the other hand, since here we're parameterizing each path by cuboid, we need to reparameterize each path as a proxy cuboid. And we actually use the PCA to find the proxy box. Okay, our PCA is not able to give a canonical orientation. In fact, if you flip the axis or rotate the axis, it's still like rotated by 100 degrees, then it's still the same box. So there are the rotation equivalent class And we actually use the axis set parameterization. So we treat the 3 axes of PCA as 3 vectors. And this is the axis set. And this axis set has no order of the axis. And later I will explain some other tricks as well. But basically, with a very careful design of the rotation prediction, we are actually able to achieve very strong cross-category transferability for the part rotation estimation. And here, the training a chair and test the table, bed, and cabinet. We use the predicted rotation to assemble the cuboids into objects. And you see that the test categories, the assembling resembles the input image, which is the evidence that the rotation is well predicted. Okay, now we have the orientation of all the cuboids, and we will next predict their size. Right, so we have the input is the image, the part mask, which is very important, and then the axis of the 3D cuboids of the part, and we just predict the extent along each axis as the size. Again, with certain tricks, for the sake of time, I'm not explaining, but you can check the paper. It's possible to actually predict the size reasonably well. It's not as good as the rotation, because from single image to reason the size is a difficult problem, right? There are perspective effects, but the result is reasonable. And then part assembly. So we have the single parts orientation, size, and next we're going to reason about the relative 3D position of 2 parts. Okay. We actually only reason about the adjacency parts. First of all, we're able to, from the image, predict adjacency of parts. And once we're able to predict adjacency, we will reason about their spatial relationships using the contact point as a connection of 2 parts. So basically, we'll parameterize the relative position of each part to the contact point between them. Okay. And here, we make a simplified assumption that there's a single contact point. Okay, and if you're able to predict the relative position of each part to the contact point, then we can rebuild the relative position of the parts centers. In fact, the parameterization of the parts are through their centers. And then we can assemble them. And the good news is that, describe the network input is image, the masks of the 2 parts, an axis set, which is actually just the orientation representation of the cuboid, and then the part size. They are given to the network, and we predict the relative position of cuboids. And the transferability is actually still good. Maybe you don't get a sense of the units, the numbers, because you're not clear about the units. But let's see some pictures. With the pictures, you can still see that parts are well assembled together. Right? You see that after assembling them together, they actually get us on novel categories, the structure resemble the input image as reference. So the relative position of parts using the parameterization of part location, part orientation, part size, with this kind of information, they are reasonably predicted. To justify that, this is really a transferable zero-shot assembly pipeline. We show some more interesting results. Right, this is a 5-star, this 5-angle star, and this like a simplified door or fence. And you see that for those that are completely unknown objects to the algorithms, they are also able to reconstruct the 3D structure reasonably well. Although I would say that stronger relationship pairs could be added to make the results more beautiful, like symmetries. Okay, and maybe I'll be very fast to talk about the key technique. One of the key techniques is to handle the rotation. And recall that we introduced the active set parameterization. The reason is, as I said, like there will be rotation, I mean, like the ground truths are from PCA, right? And somehow using a box to represent a part, there are ambiguities, and you need to handle it. Otherwise, for similar appearance of paths, they have very different ground truths, and that will confuse the network. Yeah, so cleaning the data here is a very difficult step, but it's the way is we use active set to represent the equivalent category of equivalent class of the rotations. So then for the ground truths or the prediction, the rotation are just the 3 vectors of the frame. The rotation is represented, or the rotation equivalent class. The rotation equivalent class is represented as the set of the 3 frames. Okay, and then it becomes a set comparison problem. We can use the matching loss to achieve the task. That's the loss construction. And a more challenging issue is active set is actually just a re-parameterization of rotation. In fact, rotation equivalent class. However, for the rotation group, it's not diffeomorphism to the open set in Euclidean space. And for some kind of a deep mathematical reasons, it will cause severe local minimum issues for network training. Okay, so today, if you're trying to regress the rotation, there are many tricks. There are actually not many. There are some critical tricks to apply. And for our access set problem, similarly, there are important tricks to apply. And the trick is to use the mixture of expert. It's like there we use a network of several branches to predict the several candidates of the access sets. And then also for each candidate, we predict the probability for that to be the ground truth. Okay, and then we actually use a mixture of a Gaussian kind of loss, log likelihood, a mixture of Gaussian kind of loss to compute the probability of the likelihood of the log likelihood of the ground truth notation. And this way, we're able to address the ambiguity, the local minimum issue in training network. And here we show the results that using the access set representation and the major expert, we're able to achieve a very strong performance in a zero-shot transferability setup. In fact, for the case that is not transferable, still it's better. The transferability is more like from a correct decomposition of the whole system. Okay, then let me just show some results. Like we are comparing some different methods and bullet our own approach a bit. This is the test of the chair data, which is not so interesting. All methods seems to do a reasonable job. And the challenging part is the tested data is from a different category, right? The C, especially here, it's a bet that ours perform reasonably well. Then the C, the second best approach is this naive GCN. Okay, so graph neural, this is a kind of a graph neural network implementation. It's based upon the NeurIPS 2020 paper that builds a graph neural network for each part. For each part of the object is a node, and then for adjacencies and paths, we have edges to connect them. Not we, they have edges to connect them, and then run the graph neural network to predict the orientation and size of the cuboid. Sounds like not much different from our implementation, but there are actually certain critical differences, which is like their part level prediction design is incorrect or not as effective as our approach. So there actually is a big performance difference. Now, if you will replace the end-to-end GCN pipeline with the access set and access length parameterization techniques we are introducing, still train it in an end-to-end manner, the GCN performance could also improve quite a lot. Okay, but they are both much better than like end-to-end, like sorry, the fully convolutional, like pixel level convolutional approach without recognition of paths information. So here the message is, first of all, you need path and path relationships, and secondly, you need to create all the modules correctly, otherwise it still won't work. Last work is to show the usage of 3D paths for synthesizing portrait images. Here's the results of our approach. You can think that first of all, it's kind of like a GAN work, the generative adversarial network. Right? Many people use GANs to synthesize images and here faces, and here we're also using GAN. Now the interesting part or the different part is that we're able to actually give view consistent results. By changing the view, we don't lose the identity of the person, and then also give like a detailed controlment of the paths. You can decide to change the style in terms of geometry and texture of like the eye or the lips or like the nose. Okay. So to be able to achieve part level controlment, we need parts. Okay. To be able to give view consistent results, we need 3D. So put them together. This is a 3D. This approach, although its generation is on the image plane, it actually has a 3D path-based latent representation. Okay, so here we simply decompose the face to hair, lip, cloth, skin, brow, and neck. This kind of simple paths, but they are represented in 3D. I will show you how we did it. Okay, so first of all, talk about the baseline, right? Style GAN could be thought as a state-of-the-art image generator. It's also claimed to be able to control the style of the generation, but its control of style is a bit the styles are emerged from the training process, and in fact, it's a coarse level controlment of the generation process. Is by scaling the image features at the convolution layer with incoming style vectors. But this is really a pioneer work, and our work is based upon it with a 3D and part-based ingredients. Okay, and we are able to control in a more targeted way. Sorry, first explain the limitation of style GAN a bit. Like when we're trying to control the pose of the face, you see that the lips gets open, right? And we'll try to control the age of the person, the expression changes. This is just not something we want. We do not want the effects to be entangled. And the ideal way is to disentangle different aspects of styles and then control them individually. Yeah. So our approach, we decompose the generation space into two individual subspaces. One is the geometric space, the other is the texture space. And then we in fact design a novel SOF GAN. And here, which is a short for semantic occupancy field, which is a way of representing the 3D path information, a volumetric way of representing the 3D path information. Okay. So in this space, we model we use the geometry code to model the distribution of 3D paths. And then on the image space, we stylize the paths to vivid textures. Okay, next, let me quickly introduce the pipeline. Now, unlike traditional, well, this is a big pipeline. I'll introduce it component by component. Unlike traditional approach of generating images from a single latent vector. As I said, we actually have 3 codes: the texture code, the geometric code, and the camera codes. They can be controlled independently. For the geometric part, we sample a code from the geometric space and then generate the 3D volumetric version of the part information. And then this 3D part information is projected space. And then we use a style gun kind of a approach to stylize the rendered segmentation map. Okay. So let's first introduce the semantic occupancy field part, the semantic occupancy modeling, and how we train the geometric space. I'm sorry, here. So we propose SOF portrait representation. This approach is not the signed distance or the occupancy, because the signed distance and occupancy, they are just a pure geometric. Instead, we also wanted to have certain semantic information. So it's for every voxel in a space, we will predict the spatial feature vector. Okay. And then, in fact, we're using a way like in NERV, to do remarching to render this semantic part information to the image space. So this way we get the part mask. Okay. So for the training of it, we actually use a supervised learning approach, which is also very different from style GAN, which is like just a GAN type of approach. We can use the synthetic data with the part mask or the real data with human annotated part mask. But basically, like how people train the nerves, you have the image space part segment information, and then you would learn the SOF, the 3D latent representation, so that the remarching will give you this semantic part onto the image. And here the visualization, because in the 3D space, they are the part information. You can find the boundaries between the parts, and we can actually use the Martian cube to reconstruct the surface between the parts. Okay, that's the part for us to build the SOF. And next, given the semantic maps to project on a view, we're actually able to stylize it to become a vivid picture. So here we also have certain tricks. It starts from this, you can think it starts from this part map on the view. And then we will try to assign random style vector to each part, stylize it using the style gun kind of approach. The trick is we actually invent a technique called the style mixing, which is to reduce the complexity for training, like varying a lot of different possibility of the style vector for each part. For the details, you can refer to the paper, which is the TOG paper. Here is the architecture, probably due to the sake of time, I'm not going to explain the details. And here's a comparison for the inputs of our approach versus different baselines. Also, I have to skip it probably. For the rest of the time, maybe I will just show some pictures. They are also the pictures to show that when you change the viewpoint, but to preserve the style and the geometry codes, the texture and geometry codes, you see that the identity of a person is actually preserved. In fact, the geometry is also basically the same. And for the style mixing training approach we introduced, we're also able to achieve more robust result. Now here's an example that if you are not giving all the parts of the face as input, which is the last row, just give some parts of the face as input, we're still able to synthesize well, whereas the baselines, they are not able to do robustly. Okay. And then finally, there are certain videos to show the results. And here is this region is what you want to change. It's like the mask. You can decide to change the whole face, or you can decide to change just a part of the face. Now we are only changing the background, and you see that for the census result, the foreground is preserved, but the background is changing. And then you can decide to change the style of the face. And this is mask, and you see that like the appearance is changing. This is this will change the hat. Right. Okay, and there's the example. Actually, you've seen it. Let's see a different example here. You see many more examples of changing the pose. And then this is an example that if you have you can copy the style from a video. Okay, so that's it for this work. I also would like to emphasize that this work is done by my visiting student An-Pei Chen, and the largely in the lab which is advisor, Professor Jing Yi's lab. Okay, to summarize the future work, and from the whole presentation, I just want to deliver information that the neural network saved us some efforts for feature and predictor design. Now we're able to learn features. Okay. However, if you want to want the ability to have a compositional generalizability, then identifying the modules and their interfaces is important. And also for the end-to-end learning, it's important to find the right form of modules for downstream tasks instead of simply being interpreted as using gradient descent. Okay, so although network is able to discover features, having a certain kind of principles for module design is important. And here, part is an important such kind of instructive principle. Okay, that's it for my presentation. And thank you for your patience.
Thank you. Thank you for the great talk. And that's really impressive work that you have presented. We have some questions in the chat. First one is, in the first work, how to define ground truth clusters, as the low-level clustering is sometimes not obvious or straightforward. Do you need to define a few primitives? I also see in a few arguable ground truth segmentation results. For example, a bar at the back part of a chair is split into multiple segments.
Thank you. So first of all, here we also use the partnet as the training data. So partnet has the semantic parts annotations, and you can think this way. Of course, another approach to define primitives. However, when you define primitives, you face the question, like in the traditionally people like to use like cylinders or cuboids or spheres as the primitives. But you may ask, can we have more fancier, like a more complex primitives, right? It becomes a difficulty of how to define the primitives. And here we use the partnet labels. You think that you are learning the primitives. Yeah. This is answer to the first question. The second question, will the path segmentation method be robust to arbitrary rotations? Still work one, right? Hello? Yeah, is it still about like, I assume that the second question, will the path segmentation method be robust to arbitrary rotations, still targeting at the first work? Well, at the part level, we are actually treating each part as a point cloud. Okay, so whether it's robust to arbitrary rotations, it should be dependent on the choice of your network. I mean, for example, there are many equivariant neural networks for point clouds, then they would have better robustness to rotations. And here we actually are just using the point net. So whether it's robust rotations will depend on the data augmentation you take. Yeah. The third question, can part segmentation and part assembly facilitate the 3D shape classification? Oh, that's a fantastic question. We haven't done this kind of experiments. However, I do believe they will, because because when we're talking about novel shapes, right? Suppose we're talking about like the classification of novel shapes, then perhaps they are just the shapes you have never seen, whereas they have consistent or coherent structures. If we are able to extract the structures and then classify based upon the structures, maybe they will be more robust than classifying based upon local features. Yes. Especially, for novel category objects. Will there be a scale ambiguity when performing 3D reconstruction based on a single image? Yeah, the last question is also an excellent question. So when people talk about a 3D reconstruction, single image reconstruction, we all know that the standard practice is to put the shape in a canonical space, which normalize the size. And here, we also did the same, like to put the object in a canonical space. But I would say from our experiments, we find, predicting the rotation, if you check the paper, you'll see predicting the rotation of the path, they get very good transferability across scales. In fact, even not in the same category generalization setup, the accuracy is also good. Like for the part size, this is very difficult. Although after our many struggles, we also get the reasonable results. I feel to some extent it's also already pretty good. The error is obviously larger than rotation. I feel like the scale ambiguity you are mentioning here is creating big trouble to the prediction of part size. For this reason, we think that predicting the relative size of parts will be a promising idea. However, we also find it's not so trivial. So addressing the scale ambiguity is an interesting and challenging problem.
Yes, perfect. I also have a follow-up question. So I wonder if the part segmentation would highly depend on the data complexity, because for the ShapeNet part dataset, we know that for the highest level of fine-grained segmentation, there will be some common part categories that occur only in a few samples in the whole dataset, and it will be hard to recognize them in a fine-grained manner.
Yeah, that's also a great question, I would say. For example, we are using the, I'm not putting the table here, but in fact, in the paper, we actually tried to evaluate at different levels of the part net, like different levels of part net. And the interesting part is, you might be wondering like whether it's easier to do the transferability at the coarse level or the fine-grained level. Now they both have their own challenges, right? If you define the part to be at like the coarse level, the challenges you might be thinking about a very much semantic parts. Then the very semantic parts will not be transferable.
Yes.
Whereas if the part definition is a bit low level, then it's getting closer to the primitives, and then it becomes more transferable across categories. Yeah, there's this question. Yes. Also for the part net annotation, when we were annotating the pathnet, we are already preparing to start the Sapien project. If you know the Sapien project, that is the project to use the objects for robotics. And there in order to label the paths for Sapien, at the time we decided that we will go to the kind of primitive level, because when we try to model robotics, we need the mobility structures, right? Maybe assemble paths into objects, this kind of challenges. So we need a very fine-grained annotation. So that actually also supports this paper, to test the transferability. Somehow at a more primitive level, it seems like it's more reasonable to use our way. And then, sorry, just add one last point. For this work, we justified that isolating the path of interest from the rest, or be very conservative in a context, is helpful. However, this is just the extreme of being conservative in adding a context. And we probably are too much extreme. So adding a certain context will help to disambiguate the possible ways of segmenting paths as well. So then it actually is a question of how to reasonably add some context to help the decomposition. Like you can think the traditional network is too much context, whereas this approach is no context. In between, there'll be how to do it. Yeah, that's an open question.
Thank you for the fantastic answers. So any questions from the audience? I think there's no questions, and thanks again for the great talk and for your answers, and let's keep in touch. Thank you.
Okay,
Thank you.
Thank you.
Okay, I think today we have completed most of the contents from our speakers, and now Ziwei will give a closing remark.
Sorry, seems like Ziwei is muted. Hi Ziwei, are you able to unmute yourself? Okay. Still cannot hear. Okay. Yes, can hear you now.
Okay, yeah, okay. Okay, so thanks for all these amazing speakers and sharing sessions. So I will just give a very quick closing remarks about this sensing, understanding, and synthesizing humans. The first issue is that actually the boundary between hardware and software are kind of blurry. So nowadays, a lot of things that software can do are actually being replaced by software, but algorithms. And on the other hand, some very hard issues in the software and algorithms also being solved by novel hardwares, like using LiDAR sensors, most 3D things, right? So when we're at this stage, we must think between both the advances of hardwares and softwares. So second is that the boundary between data collection and privacy. Deep learning is driven by the large-scale data sets, right? But nowadays, when we're collecting data, especially for humans, there's always concerns for privacy. But the researchers have come up with some solutions, like using simulator or just using other crowdsourcing ways. So we also have to think about this. How can do good data collection and also care about this privacy? So third is the boundary between synthesizing and reality. We're heading towards the metaverse. A lot of things can be synthesized quite good. So it's actually a time for us to also distinguish which is real and which is fake. And finally, I would like to thank our amazing organizer team. So without them, this organizer won't be successful. And thanks again to my fellow organizers. Okay, thanks you for coming. And I think all the slides and also the recordings will be posted to our workshop website. And hope to see you next year. Thank you.